Okay. Okay, well, welcome everybody to this hands-on tutorial on computer vision and real-time deep learning for object detection. Before we get started, I wanted to see if you can hear me and see me okay, and if you can see the screen okay. So if you could maybe unmute for a moment and just say the number 3, that would be awesome.
Number 3.
Number 3.
Number 3, okay. Awesome, louder, yes, great. Okay, well, it's a great honor to be here at KDD 2020, giving you this tutorial. And I want to take a few moments to introduce myself, to give you an overview of the tutorial, and tell you why you should stay for the rest of the tutorial. Now, my name is Jimmy Shanahan, and I'm based in San Francisco. I run a small consultancy here in data science and artificial intelligence, do a lot of work in data science, traditional data science applications, as well as AI computer vision applications. And I also teach at UC Berkeley. Liang Dai has helped me out with some of the content here today, and he's a research engineer at Facebook. Now, computer vision is a subfield of artificial intelligence that trains computers to interpret and understand the visual world around us. For a variety of downstream tasks, such as self-driving cars, checkoutless shopping, smart cities, cancer detection, and so on. Now, though the field of computer vision has been revolutionized by deep learning over the past 10 years, today we're going to focus on a subfield of computer vision, and that is object detection, which has also been revolutionized by deep learning, as we shall see. So, just to give you a sense of what's in store today, we are going to start here with a brief intro and logistics. And then we're going to talk about computer vision and object detection applications. Then we're going to go back to school for a moment, and we're going to look at some of the raw material that goes into building computer vision systems that can do object detection. Can I ask you to mute your mics? Just can you do a cross check to mute your mics? Or Penyang, can you actually mute people's mics if they're not muted? There's a bit of background sounds going on here.
Oh,
so thank you. So we have, I think it's kind of really important for us to understand the basics before moving into high gear to use deep learning to do object detection. So some of the basics include just a general understanding of computer vision, sliding windows. A typical example for building computer vision-based features is histogram of oriented gradients. Then we'll see how support vector machines played a big role in moving computer vision forward, especially in this field of object detection. We'll talk about image pyramids, so we can work with images and objects at different resolutions. And finally, we need to apply a suppression step because we get an over generation of candidate objects regions. So this whole field of deep learning is also being revolutionized by object detection, in the sense that it's making more demands on deep learning architectures and loss functions. So we'll take a moment to look at a multitask loss function because they're very prevalent in computer vision and other application areas of deep learning. Now, again, I'm going to pose a puzzle for you halfway through here and talk about sliding windows and image pyramids, and say, I issue a challenge to you and say, hey, how do we code these up within a deep learning framework or architecture? And I'll give you the answer as well. Then once we're all teed up, we're going to delve into object detection deep learning style. Within that whole arena, we'll see that there are many ways of doing object detection. There are two primary categories. There are two-stage approaches and single-stage approaches. And over the past 12 months, there's just been a whole new wave of object detection using deep learning approaches, and I'll tell you about those as well. There are many opportunities, as you can imagine, for object detection using deep learning, but there are also many challenges, and I'll talk about those towards the end. So when we think about object detection for the purposes of this tutorial, we're going to focus on predicting a set of bounding boxes and categories, labels for an object of interest, be that in an image or be it in a point cloud, so 2D or 3D. This tutorial will primarily focus on 2D object detection, although I'll mention in passing a couple of approaches that allow us to do 3D object detection. So what we mean here we've got a photograph, and there are two objects of interest here. There's a person and there's a bicycle. And we're very happy if we can isolate these objects by using these rectangular bounding boxes. So this gives us the what and the where, and we also get a probability as well, generally. So why is this field interesting? You know, what is, can I ask people to turn off their cameras, please? Otherwise, there will be some clutter on the slides and it'll obfuscate some of the slides. So Yao and Raul and Molly, if you can just switch off your cameras, that would be awesome. Thank you. So when it comes to why this field is suddenly exciting and why we're suddenly solving problems with computer vision, where 10 years ago we weren't making that much progress. The best we could do 10 years ago was maybe detect faces in photographs using still cameras. Today we can do a lot more. So just to give you a sense of the progress, here is a typical benchmark problem that we use in computer vision and in object detection also. And so the idea here again is to find objects and localize them within images. And in the pre-deep learning era, we saw that if we were using histogram of oriented gradient approaches, along with some machine learning techniques, we could get a 21% mean average precision on this 20 class problem. This and so until in 2012, we saw the advent of deep learning in a big way. And then we saw the MAP jump to 58 to 86. So by 2015, we had already kind of pretty much solved this problem here. So this is a small problem, 20 classes, and there are about 24,000 images, let's say about 20,000 images with about 27,000 annotations. And typically they're split between 25, and 50% test. Now, you might say, wow, this is amazing progress here, but it's a really small problem. The next problem I'm going to talk about is another benchmark problem. It's called the COCO object detection dataset that was originally put together by folks at Microsoft. And this is, if you want to take a screenshot of one slide from today's tutorial, then I would just take it of this. And this is kind of one of the key summary slides as well. So I'm going to unpack it slowly here. So on the x-axis here, we've got a variety of object detection approaches. And we also have a kind of a timeline going here from the 2012, 2015, all the way up to 2020. On our y-axis here, we have the mean average precision on a test data set from the COCO database. And on the left here, we have the more traditional computer vision approaches to object detection based upon this HOG feature, which we'll talk about momentarily. In 2015, that's 5 years ago, we really saw deep learning hit its stride in terms of object detection. And what we're seeing here is there are two main families of approaches to object detection using deep learning. One is based upon a two-stage detector. There are 2 steps in it. And then the other is basically a one-stage detector. And the 2-stage detector here are all the black bars. And as you can see, we've made steady progress. And 2-stage detectors kind of paved the way for deep learning approaches. Obviously, if you can do something in one step, you prefer it over 2 steps. And people started experimenting with single step approaches here pretty early on. And what we can see here is that the state-of-the-art approach for this particular data set right now is running at 55% MAP. We've come a long way from, say, 15% or even 5% 5 years ago. And so the single stage or one stage detectors are starting to take over from these 2-stage detectors in this particular data set and in general. Now, there's one more take-home message here. You might say, well, what is this guy doing over here at 45%? Well, this is a transformer-based approach. It's one of the first transformer-based approaches to deep learning that has really, not only have we gone from 2 steps to 1 step, we've gone to 1 step with little to no background knowledge required in order to do object detection. So I see this as a really exciting approach, though it doesn't deliver the goodies yet here in terms of MAP. But we'll look at these approaches, these efficient det and deter later in the tutorial. And we're going to spend some time talking about each of the families here, just to give you a sense and give you some background so that we can understand better where things are coming from and where they're going. So if there are any questions, please send them on the chat. I think that I will see them, and Pen Yang will also see them. He's our student volunteer who's doing an awesome job here, and he will alert me as well. So we'll look at this pre-deep learning approach here, just because we'll learn a lot from it. And then we'll see how these approaches influence the earlier 2-stage models and even the single-stage models as well. And then we'll finish off here by looking at these more recent approaches that are really exciting. So not only is MAP important on various benchmark problems, but it's important that we have pipelines that are efficient. So here again, we've got X and Y axis. So on the X dimension here, we're talking about the floating point operations that these deep neural networks require in order to process an image. And on the left, on the Y axis here, we have the average precision on the benchmark COCO data set that we just looked at. So as we saw previously, this COCO data set has about 80 classes that we're interested in finding in images, and we've got about 150 to 200,000 images that we can play around with in terms of training, test, and validation. So here there's a variety of families of object detectors displayed here. I'll just highlight a couple here. So we have this YOLO family, which we'll spend a bit of time on today because it's highly instructive for us, especially if we're new to object detection and especially if we want to get in and kind of code these things up from scratch, because they're kind of very accessible, and with a bit of passion and a little bit of time, maybe a couple of days, you can actually build out this kind of baseline approach here, which is really illustrative and an awesome thing to do. So this is the YOLO family here, and we can see that the YOLO has, MAP performance that's down at the lower end here in the 30s, and whereas our efficient det detector that we just talked about previously is up here in the mid-50s. And we also have these feature pyramid networks, which we'll talk about. There's RetinaNet, and then there's also this NAS FPN and others here as well. These are all based upon feature pyramid network architectures, which are also very powerful. But again, I'll just highlight that the efficient det here, which is also a feature pyramid network with a twist, gives us really amazing performance, not only in terms of MAP, but also in terms of computational complexity. So the bigger our network is, the slower it is, but the better performance we get here in mean average precision terms. So we had a question here, and the question is, what is the difference between 1-stage and 2-stage models? That is a great question, and you know why? I've got 1,000 slides here to give you the answer. So if you bear with me for the next 2.5, 3 hours, you're going to walk out of here knowing exactly the difference between 2-stage, 1-stage, and many other things as well. So thank you very much for your question. I appreciate it. Okay, so we can see that when it comes to computer vision and object detection, many things are important, including MAP and the computational requirements and memory footprint as well. How big are our models? Is our model 10 meg or 10 gig or 100 meg? These are all big considerations when you're looking at devices that might be like a cell phone or a camera that we want to make more intelligent. So another way to look at this world of computer vision is timeline here, chronologically. So over here on the left, we've got the pre-deep learning era. And again, there's a whole variety of approaches here that have been developed over the past 2 or 3 decades. And it wasn't really until the 2005, 2010 timeframe that we started to make some real progress here. And even the SIFT features here in 1999, they were also a big breakthrough as well. But on the right here, we've got these deep learning approaches. And so in a very short time, we've gotten up to speed and gotten way ahead of these traditional pipelines. So today, we're going to look at a variety of 2-stage approaches, and they'll primarily come from this region-based convolutional neural network family. And so this is the kind of baseline approach, and then has been modified to give us the fast RCNN, faster, and mask RCNN down here. And that's a 2-stage approach, and we'll go into details. Then we also have a single-stage model or 1-stage model, and beginning with overfeed and YOLO is a good example, RetinaNet and FPN and so on. And then I have this third category, which I call the third wave, or the new wave of approaches, which have come about over the past, say, 12 months or less, maybe 6 to 12 months. And here I highlight efficient depth and detection transformer, DETR. And so these are some of the approaches that we're going to cover. And so this is why you should stick around and maybe figure out what are these approaches and how are they different. So also I'm going to argue that this is a pre-deep learning person detection pipeline. It's a 5-step pipeline. So each step is kind of independent of itself, of each other. And so the first steps here, take an image, and then we would basically do a multi-scale version of the image. So we would downsample the image to give us different resolutions, and then we would take each of those images at different levels, and then we would pan a sub window or slider window across the image to give us a crop or a subset of the image that we would convert into a feature vector. It could be a simple feature vector of pixels that we might pass on then to a support vector machine, and then the support vector machine might say, oh, that's a person or not a person. And as you can imagine, that sliding this window across one image or each image in this image pyramid here will generate lots of potential people candidates or region candidates. And so then we need to go do a post-processing step where we say, let's try to suppress regions that are overlapping and do that in a smart way. And we might end up with an image like this. So this is a 5-step process. So by the end of today's tutorial, I hope that you'll see that we can maybe reduce this 5-step process down to a single pipeline. And it's 1 step, but it's also a single neural network. Now, we talked earlier about 2-stage, 1-stage, and this is going into a very fine subtlety here, where this 1 step here, this DETR, is a good example of a 1 step where there's little to no background knowledge or post-processing steps required. We'll see that our 2-stage approach to object detection requires a post-processing step, this non-maximum suppression step. So do most of our 1-stage approaches, but this DETR here eliminates this step altogether. So in other words, we have a 3-step, 2-step, and then a 1-step approach. So I kind of maybe misled you earlier, but when in the field of object detection, people talk about 1-stage, 2-stage, and they kind of this final NMS step here is kind of bundled in there. And I always want to make sure that we separate this step out very clearly, because DETR does not require this post-processing step. Okay, so this is kind of another, just a kind of overview of the traditional pre-deep learning approach to object detection. And we do our image pyramid, we construct some features for each, I guess, crop within the image, and then we pass it through a support vector machine, and we do our NMS step, and that's good. So 2005, this was state of the art in terms of object detection. But we've come a long way. And like I mentioned, the momentum right now here is going from 2-stage to a 1-stage detector. And I want to just give you a sense of what that means, so that you're going to stick around and learn about how we do all this stuff. So at a high level here, and again, this is high level, we'll get into details subsequently in the tutorial. These 1-stage detectors is kind of where the money is at the moment. And this 1-stage detectors really have started to overtake the 2-stage approaches based upon a very simple thing. So if you think about image classification, say cats versus dogs, we take our input image here, we pass it through a convolutional neural network layer by layer, where we would downsample in later layers in the network. So we go from the full-blown image here down to a feature map here that might be 1/8 of the size or 1/16 of the size of the original image. And then we might do a fully connected layer, and then do a classification of the image. So that's a traditional classification architecture. And so the idea here is to say, okay, well, as we go down into the network here, we're kind of, we got out here, we got the pixels. And here we've got maybe a higher order version of a pixel. And then as we go in here, we've got some higher order features. So we have this kind of bottom-up approach from the pixel data here. And the idea here then was to infuse this bottom-up features with some top-down pathway-based features. So as you can imagine, the features here at stage 4 are in the feature map are going to be super rich with information. They're going to be pulling information from a big area of the input image. And so they're viewed as kind of top-down and very rich. So the idea was to take these bottom-up representations, fuse them with these top-down representations, and then do predictions on this basis. And I know this maybe makes no sense at this point. So this is we're jumping right into it here, but this fusion of bottom-up feature maps and top-down feature maps is kind of revolutionary, and we call this a feature pyramid network. And we'll talk about this over and over and over today. So we refer to this as FPN. And so at an abstract level, we can see our single stage object detectors being viewed as this kind of backbone that we traditionally have for classification. Think of ResNet, for example. And then this kind of this feature pyramid network here, which we refer to as the neck, where we fuse the bottom-up features and the top-down feature maps. And then we do our predictions. So these are 3 phases in our network here. And so I just want to get to the punchline here. The main progress has been in this neck part. I mean, there's been progress here as well, and here, but here has been the really big mover in the last couple of years. So RetinaNet, which we'll talk about later, definitely falls in this family of feature pyramid networks. Here's our backbone, here's our neck, and here's our heads. And efficient det. I know you don't want to see this right now, but I'm just going to give you the kind of very quick summary of what efficient det, which is the state-of-the-art approach to image or object detection at the moment. And so the idea here, here's our backbone, here's our neck, here are our heads. And so efficient det focused on saying, look, instead of just merging layer feature maps from the bottom-up pipeline with the top-down pipeline, using, say, element-wise addition, just simple element-wise addition of 2 feature maps, let's do something more sophisticated. So these folks at Google said, hey, let's go search out a better aggregator in the neck part here. And once we find a good, this layer here, this is a bidirectional feature pyramid layer that they have discovered using a search algorithm. Once they found this, they said, okay, well, why not just repeat this multiple times? And when you do this, you get all these different versions of efficient det, 0, 1, 2, all the way to 7x. And that's where you can see that this aggregator layer here is repeated, in this case here, 3 times, 6 times, 8 times, and so on. So, all right. So one more exciting piece before we get into the weeds of today's presentation. So this is the transformers approach to object detection that was just published in May 28, just a couple months ago, by some folks over at Facebook. And this is the punchline here. Again, I'm trying to give you a reason why you want to stick around and understand and learn about these things. And so basically, this is the DETER framework. And it's a transformer framework where we take our image, push it through some backbone system here, get our feature maps, flatten those feature maps so we get a whole bunch of pixels. Think of each pixel here as a word that is represented as using an encoding. We pass it through our transformer, and then each pixel is output here using a new embedding. This is passed on to our decoder, and then the work of our decoder really is to say, look, go find me some bounding boxes out here. A bounding box is defined by the XY location and the width and height. And so the decoder here has to figure out how to decode some bounding box queries. And so you can see the different phases in this detector. So this is a revolutionary approach. And the big things here are you don't need to provide any background knowledge that we might need for some of the other approaches that we'll talk about. These include anchor boxes. They include the post-processing step. Then they also include the how do we match up the ground truth with our network predictors and so on. And of course, using transformers. And then there's a big move here also in terms of the loss function. We have a different way of doing the matching within our loss function. And there's also the use of this generalized intersection over union, which is also an interesting twist. So all this adds up to an exciting framework, which I hope you'll stick around and learn more about later in the presentation. So as you know, there are notebooks that I prepared for this tutorial, and they kind of run the gamut here from looking at computer vision 101. Let's say you're a rookie on computer vision and you want to learn a few basics here. Here I talk about those. I also talk about different libraries that can be used, and also how we can move into the deep learning realm. How can we go from raw image pixels, computer vision libraries into the deep learning realm. Then I have a notebook here that tells us about how to do histogram of oriented gradients using support vector machines. And I also frame it out, instead of using a support vector machine, I say, hey, let's go use a convolutional neural network. And I set up a nice little problem here, and you can run this very quickly, easily on your local machine if you don't have a GPU. Then there are, if you're new to convolutional neural networks, there's a whole folder of notebooks here which will kind of ease your way into this and give you some more background with some great examples, including LONET and AlexNet. So you get to build AlexNet from scratch by yourself. Then there's a couple of notebooks here about YOLO V1, RetinaNet, DETER, and efficient det. And we're going to spend a chunk of time here in YOLO V1 because it really helps us internalize a lot of the fundamentals that will kind of can be used in all of these approaches here, and you'll appreciate more of what's going on here. It's also an opportunity here to see how to do some tensor programming. And so it's kind of like saying, hey, I'm going to write all my code in terms of NumPy operations. And so this is kind of important here, and it's important in the sense that we have loss functions that are really complicated, and we need to be able to kind of access different parts of our output tensors in different ways. So these are the notebooks, and if you really are a novice, these are some more background notebooks on just neural network basics. So to give you a sense of what's in store here in the notebooks, here's our histogram of oriented gradient-based notebook, classifier notebook, and the link. So Penyang, can you paste the link to the notebook in the so okay.
Sure. Yeah.
So I'm not sure how to. So it's on the website for this tutorial. There's a link to a master page for this tutorial, and there you'll see a QR code, and you'll see links to notebooks and videos and so on. So this is kind of our pre-deep learning days. This is how we would have been doing business, and this is kind of like a modern day pipeline via Dieter. And if you are new to deep learning, then I think that it's important to know the basics. And for me, a basic operation is saying taking an image like this and being able to go to a feature map like this using a single operation. So here I'm going from 400 by 400 by 3. This is my input image. And then I want to get output here, a feature map that's 4 by 4 with a depth of 64. So I would encourage you to think about that problem for a moment and see if you can solve that one. It's pretty straightforward. I need to have one way to do this is to say, look, I'm going to take a 100 by 100 kernel with a stride of 100, and I'm going to have 64 of those, and this will give me this output feature map. So we need to be able to think about these things relatively quickly, easily, so that we can not get stuck with these kind of simple operations. So this is kind of important that we kind of get these down. Okay, so I did talk about YOLO v1 earlier on, and here is the architecture. Matthew, can you switch off your camera because it's going to block some of the slides, I think, when it's recorded. Thank you. I apologize that's kind of the case here. I don't know how to change the setting otherwise. Of course, it's nice to see you, but I think that I can't do that and record the video at the same time. So we'll figure out over the break here. I didn't mention that we will have a break here, probably about an hour and a half into the tutorial, if that's okay, if people want a break. Or is it like, so in Silicon Valley, we say if you stop for lunch, you are lunch. So I'm not sure if people want to have a break today or they feel a little bit nervous about the whole thing. So anyways, here is the YOLO architecture. And really, it's a very straightforward architecture in the sense that we're going from our input image here through our convolutional layer as a fully connected layer, and then our output feature map here. And then we have some post-processing steps, which is the NMS step that we talked about previously. Here is some code here. This is PyTorch, and here's our loss function. So hopefully by the end of today's tutorial, you'll be able to look at these things and say, I understand this kind of loss function. I'm not freaked out by how complicated it is. I can unpack it, and I could code it up also. And architectures, well, you'll probably say that's a baby architecture by the end of this 3 hours. And oh, PyTorch, well, it's pretty straightforward. So, all right. So I guess coming into this tutorial, I'm not sure if you guys had time to watch the videos offline. If you did, that's awesome. And if you didn't, that's not too bad either, because the videos are sticking around, I believe. And you are here today. So I'll give you a sense of kind of what you missed here. Sorry, I've lost my mouse. Can't see it. sorry. So these are videos that I prepared up front, and I know that some of you have seen these videos, and that's great. That's great to get warmed up. And as you can see, that you know, what we're trying to do here is going to try to present object detection, which is ordinarily a semester-long course, let's say 45 hours long typically, and we're trying to compress that down to 3 hours. And so the idea here is not to teach you everything, but at least to give you enough of tools so that you can go out there and learn the rest by yourself. And so I seem to have lost my mouse for some reason. I can't see my mouse anymore. Okay, got it back. All right, so if you've watched the videos, great. There won't be significant overlap between what we talk today and the videos. There's a lot of material that can be covered, and we're going to cover some extra different stuff so that it won't be boring to you, if that's okay. So here's kind of how things look. We're now going to look very quickly at some exciting applications of object detection before moving on to the into the weeds and understanding some of the technical details. So as we know, computer vision is this kind of big umbrella field that is focusing on interpreting, understanding the visual world surrounding us. And object detection just focuses on a very small aspect of that, and that is predicting a set of bounding boxes and category labels for each object of interest in our image or our 3D point cloud. And it really is playing a very important role across lots of different verticals, from consumer, finance, security, retail, and so on. And if we look at our smartphones, we can unlock them using image object detection. And so we're very interested in finding objects. We're very interested in segmenting them out, counting them in different ways, different applications. We want to take satellite images and recognize various structures in those satellite images. We want to use maybe some thermal imaging, and again, these approaches can be brought to bear on these kind of images. So when it comes to healthcare, deep learning is also revolutionizing this field. And so here we've got an example of breast cancer detection using deep learning. In this case here, it's a mashup of RetinaNet and MobileNet V2. Hopefully some of these keywords here will make sense to you at the end of this tutorial. And here we can see that we've got our area under the curve. This is an ROC curve. And we can see that our AI, our computer vision-based system, is doing a lot better than the human radiologists. And this was a huge surprise. And this is a paper from Nature earlier this year. And this is a combination of folks at Google Health, DeepMind, and Imperial College in London. And so just to give you a sense, they had a multi-stage approach here. They had a RetinaNet detector, then they had a MobileNet classifier, and a variety of other modules as well that they bolted together to solve this problem. Here's another example for brain tumors, malaria infection. All these are using deep learning approaches. Maybe you've come across this face app where we try to meet yourself in the future or in the past. Here's you can tell me which version is me, which is the current and which is the past. I guess you can't, it's very difficult to communicate here. I don't see you, and you can't chat with me, and muting, unmuting is kind of awkward. You can press that space bar for, if you want to speak, you can press the space bar, speak, and then release the space bar. So left or right, well, this is me now, and this is some younger version according to FaceApp. Deep fakes is a very hot topic right now. It's a very hot topic of security and entertainment, and object detection is also playing a key role there as well. When it comes to augmented reality, we're seeing it's starting to make its way into the consumer market. This is a Garmin golf range finder for those of you who play golf. And here is the reality. Here's the augmented reality here. It's telling me where is my, where is the next, the tee, or not tee, but the green. And in say, insurance and in construction industry, we like to be able to look at construction sites and understand, what's going on there. How are things changing? Are things level? Are they up to code? And here we're seeing 3D LiDAR systems and point cloud analysis helping out. As I say, augmented reality, this is magicleap.com, and they have a really exciting headset that kind of mixes reality and virtual reality. This paper here was presented this year in CVPR. It's a very exciting breakthrough paper in the point cloud arena for object detection and segmentation in 3D data. And this is the architecture here. I'm mentioning this now because we're not going to talk about it much more later. So this is RAND LA. It's kind of a UNet architecture where we take our input 3D cloud, and here's our output segmentation, point-wise segmentation. And it does a really good job. There are a number of shortcomings, but we won't talk about those. Of course, these point clouds are very important in self-driving cars. And here are some of the components of an autonomous vehicle, and image understanding, perception, localization. All these things here use computer vision and object detection. One of the big driving forces behind computer vision right now, and object detection in particular, is trying to make the footprint of our deep learned models as small as possible. We'd love to be able to get an object detection system down to, say, 3 meg or 10 meg or less, but that's really difficult. And so it's always a trade-off between how big our model is and the accuracy performance of the model. So we really want to use deep learning on our mobile devices. We want to make our devices smarter. We don't want to have dumb cameras. We like to have smart cameras. And to do that, we need to have very simple, powerful models. Okay, so let's change gears from the meta and let's go into the weeds a little bit here. And let's tell you about object detection and some of the kind of building blocks that go into object detection before going into the deep learning approaches. Before I move on here, I wanted to see, do people have questions at this time? And again, you can use your spacebar, keep it pressed, say a few words, and then release your spacebar as an easy way to unmute. Do I take radio silence as meaning I'm doing an awesome job and I should just continue? Or has everybody left?
Just continue
Okay.
for me. Fine.
Okay, all right. So object detection. So we have a variety of computer vision type problems we want to tackle here. Here is just a pure object classification. So maybe you want to just say, hey, what are the objects in the image here? So it's kind of like just summarizing which objects are present. Over here, we have this generic object detection, bounding box detection. And then we've got semantic segmentation, where we say label each pixel. You don't have to tell me that these pixels belong to the same object. Just tell me what is the class of the pixel. And then we have this object instance segmentation, where we want the pixels to be labeled correctly. And we want to know that for this sheep here, these are all the pixels that correspond to that sheep. And this is a higher task. We're just going to limit ourselves today to looking at object detection, where we delimit the objects detected using bounding boxes. And this is just an example again. And we will not be looking at this in detail. We might just mention in passing how we can just take a bounding box detector and enhance it to give us instance level segmentation. And like I mentioned earlier on, this is semantic segmentation, instance segmentation, and this is panoptic segmentation, where we actually label all pixels in the image. Here we just label pixels that belong to objects of interest. Here we label everything. Then we can go beyond these bounding box and masks, and we can look at human key points. And this is a COCO-based key point detection challenge with some labeled data available. So we want to, we represent various animate objects in terms of these key points. And then we are also interested in modeling objects in terms of surfaces. So as I mentioned earlier on, object detection has seen an amazing explosion of interest, of progress, and of applications. And so this is the Pascal VOC data set that we saw earlier, and we saw some of these results earlier. So we saw huge performance improvements over the past, say, 12 to 13 years. And we also saw this previously. And I'd like to now to look at some of these pre-deep learning approaches, because they provide us a lot of the building blocks that go into helping us understand where do these deep learning approaches come from, and how do we go from RCNN to faster RCNN? How do we make progress over here? And so we can learn a lot by looking back in time to see how they came about. So, like I mentioned earlier, there are a variety of benchmark problems that enable us to measure the performance of our approaches. And so here I list some of those approaches, and they go from MNIST, a very simple digit classification problem, all the way up to ImageNet, to MS COCO, and down to Open Images. Open Images is this data set that was published maybe 2 years ago, and it's been updated 3 years ago, actually. That's been updated regularly, and then there are currently over 10 million images with 6,000 categories. And there are a variety of tasks that you can perform on this data set. So here's kind of a bird's eye view. This is our MNIST. This is our CIFAR 10. This is a great data set here, a small data set with thumbnail images. There's about 60,000 images available. And then we have the ImageNet data set that looks like this. And then we got the VOC Pascal smaller data set, 20,000 images. And so this CIFAR 10 here is kind of a nice little small world problem to try out different ideas that one may have in terms of architectures or loss functions or approaches to, say, classification, or not so much detection, but as I say, when it comes to object detection, we can look at the world in terms of backbone, neck, and head. And so we can certainly optimize our backbones over here on CIFAR or ImageNet and move out to object detection subsequently. So one of the most confusing things in computer vision in general is the coordinate system that we use. And so we are very used to this Cartesian coordinate system where we have X and we have Y. And when I say, and then we can express things in terms of X, Y coordinates. So when I say 2, 1, I go out 2, go up 1, and that's my 2, 1. Now, when it comes to images, we typically have an origin here up in the top left of the image. And then we've got various access patterns, which will vary depending on the framework and library you're using, or depending on the task at hand. And so typically we will view we'll view an image as a matrix. So if you're coming from NumPy programmer, tensor programmer, you'll see the whole world in terms of matrices and tensors. And typically our origin is going to be here, and we're going to express things in terms of rows and columns, rhubarb and custard. And then we'll have height and width also. Sometimes we're expressing bounding boxes. Now, if I'm coming from an annotation world where I'm, say, annotating an image and saying, hey, I found a cat here. The cat starts on the top left and it goes all the way down to the bottom right, then I might just express it in terms of X, Y coordinates, where X is this way and Y is this way. So it's kind of, you're flipping things. And so the most common bug in building these object detection pipelines is that we're flipping these things here, because typically we'll be doing our tensor programming and doing our deep learning in this kind of matrix type style. And then we'll have our annotations in this kind of Cartesian style. And we're going to have to mix one or the other. And so we tend to end up with bugs that might last for days to solve. So in terms of images, we can view images as a matrix, and where each pixel in the matrix conveys an intensity. And so if we've got grayscale images, then the intensity goes from 0 to 255, and 0 is black, and 255 is maybe is viewed as a white. And so here again is our image. Here's our pixels, and here we've kind of combined them. And if we look at this in terms of a computer program like Python, we see this array. It could be a NumPy array or something else. And one more thing that's really important again, and this is another point of great confusion. And you know, there's the channels first or channels last. And what does that mean? So when I look at an image, I may have a grayscale image, so then it's very easy. All I have is a matrix. It's a spreadsheet. But if I have RGB, if I've got a red, green, and blue colors for each pixel, then I can store those in different ways. So here I've laid out a red matrix, green matrix, and a blue matrix, and I can combine those into one matrix where this is called the channels first. So the first dimension in this three-dimensional array will be the channel, and then we're going to have the spatial coordinates here. So it'll be channel X, Y coordinate, or sorry, rows, columns, coordinates. I'm sorry. So that's one way, and then here I have example of channels last, and so both approaches to representing images and tensors are really common, and this is kind of like where your tensor programming dexterity comes out and blossoms. So the idea here is that we have our channels last, meaning that we have our spatial coordinates first, our rows and columns first, and then our RGBs will come as these vectors of 3 values here. And so that's channels last. So that's kind of important, because when we start to get into the weeds of some of these deep learning approaches, having to unpack some of the operations becomes really complicated. So what's the difference between this guy here and having a colon, comma, 0, comma, 0? Anyway, it's important to have these details out of the way. So, and you know, most modern deep learning frameworks will support both channels first and last. And I think in Keras, this channels last is the default. Now, again, if you're new to computer vision, then there are some standard libraries out there that are, you know, great, awesome, sometimes inaccessible. So OpenCV is like this amazing library. It's been a workhorse for computer vision since the late 90s, and then, but it's really difficult to get into. It's like there's good documentation, but there's a lot going on, and unless you understand how to travel through that amazing library, you're going to get lost. There is this simple CV, but it's kind of it only works with Python 2.0 or 2x. It makes things a lot simpler and intuitive. What you'll see a lot of here when we're doing deep learning for computer vision and deep learning for object detection, we'll see a lot of this this PIL and Pillow Python image library and corresponding formats. Then we also see a lot of work in NumPy as well. So your NumPy programming experience is amazing. That will stand you in good stead here. Then we have this thing called scikit image, which is kind of like the scikit-learn of image processing. And this is a pretty awesome library. So can you mute your mic, please? Thank you. I think that's probably the youngest attendee in this tutorial, I'm pretty sure. So thank you for showing up today. So these are just some of the libraries that are out there, and in the notebooks I've shared with you, you'll see examples of these guys in use. And this is really a pretty easy way into computer vision and image processing and so on. And this is scikit image here, and it's kind of got this kind of nice a montage of different ideas here, like there are images, and then you've got different operations that you can apply, like edge operators, to define boundaries between objects and so on. And we can resize and do other flipping and other modifications of the image. We can also look for some types of models, like say look for lines within images using the ransack algorithm, and so on. So then if we have multiple images, sometimes we want to say, how do we piece these images together so we can get a nice panoramic image? So I don't know if you've ever taken a panoramic image. How do you stitch those images together? Well, there's a whole art and science to this, and image registration is the key player here. And this applies to 2D and to 3D point clouds as well. As you can imagine, if you needed to take a 3D point cloud of an airport or a shopping mall, you can't just take your LiDAR and just set it up once and take the whole thing. You have to kind of go around and walk around, and then you need to stitch things together. So this registration is kind of important. And there are many other, so this is again, scikit image, really awesome, very high level, easy way to kind of get into image processing and also image processing with machine learning and so on. So Keras has its own battery of approaches for doing image for image processing, and here I just list out some of those. Like you can look at the documentation for Keras here to figure out what's available and how you might want to use it, and there's some great examples as well. So and so, you know, in Python, we're in Python world, I guess, these days. And so NumPy is a great way, and matplotlib, they have a whole bunch of kind of basic functions that allow you to display and manipulate different functions. And in the notebooks, you'll get to kind of play around with some of those transformations. So here I'm just highlighting the notebook where there's some of the basics here. Intro to computer vision, OpenCV shows you how OpenCV works, how you can manipulate images there. Then there's the PIL library, the Python image library. It's a different library to OpenCV and how you do things here. Then scaling images is really important, whether we scale the size or scale the magnitude of the RGB values, for example, how to load images into, say, Keras, and also for PyTorch, there are particular ways for setting up data sets. So, you know, maybe you've seen the MNIST data set. Well, you can load the MNIST data set into memory. Just read it and shove it in memory, and it's all great. Unfortunately, when it comes to image problems like object detection, our images are really big, and generally we can only process very small batches of examples at a time. And so we typically can maybe have one image, maybe, or we can have 32 in a batch that we can process and do learning with or prediction with. And so we need various ways to access and manipulate the images so that we can present them to the learning algorithm or to the prediction algorithm. And so there are a variety of techniques for doing this. So all these modern deep learning libraries such as Keras, TensorFlow, MXNet, PyTorch, they all have very standard way of doing things, and then they're also very extensible as well if you want to have some peculiar way to load your data and so on. And we'll see examples of these in due course. Again, if you have time, look at this notebook here. And there's just some small case study here for cats versus dogs, a classifier using this type of network architecture here. This is a kind of a backbone architecture inception net that we will use to do object detection. So I don't want to bore you with these details here. You can you know, take an image like this, and you can pass it through a convolutional neural network, and you can pass it through, say, a dense layer, and you can get out a probability, a likelihood that this is a dog or an object of interest or a class of interest. Now, when it comes to computer vision, we have a whole variety of challenges here. And these challenges here range from illumination, there are deformations, there's I can't, I'm sorry, my mouse is not letting me move my face, unfortunately, out of the way here. So there's, of course, there's occlusion here. I'm including this image here. And then there's blurring, there's maybe motion, and then you know, we can have a high variance within a class as well. These are all chairs here, for example. And so when we look at images, this is a grayscale image here. We're always trying to do some local operations on the images. And by that, I mean, we might want to apply a small, take a patch of this image here, apply some transformation or function to it, and get out a new version of the image here. So typically, we'll view this function as a kernel, and the kernel will be centered on a pixel over here in the input image, and then it'll produce a corresponding value in the output image over here. And so these kernels, these transformations were the bread and butter of computer vision for the longest time. So if I was talking to you maybe 30 years ago, you might be doing a PhD in computer vision where your job might be to build or invent such a kernel that might produce a better representation of this image than the raw pixel values that could be used for a downstream task such as classification or person detector and so on. So this afternoon, if you bear with me, you'll probably get maybe 5,000 PhDs. Each of you will get 5,000 PhDs based upon the progress we've made with these new architectures over the past, say, 5 to 10 years. So traditional approaches to object detection were largely based upon doing clever feature engineering and then passing those representations onto, say, a support vector machine. And we'll see that in a moment. And that was combined with other tricks as well, such as these multi-scale sliding window approaches. And this is some work I did back in the mid-90s I was really proud of at the time, but right now I'm embarrassed by this work. It was hard work. We were doing major feature engineering based upon color, boundary, shape descriptors, texture descriptors, and we were pushing all that into neural networks to do some classification. But we'll see that it's not too dissimilar to some of the approaches that we have in place today. So we're going to talk about this HOGS plus SVMs as kind of a representative pre-deep learning approach, just to give you get you familiar with that 5-step pipeline. And so you may have had one of these cameras, or maybe you've seen one of these guys in a museum. Well, this is how you would take photographs in the old days. You'd have a camera, and you might have some face detector here that allow you to auto focus on faces and so on. And so this is our 5-step pipeline here. We take our image here, we might downsample it and blur it basically, and then operate at these different levels here by taking patches from these different images, vectorizing or featurizing these patches here, or crops, and getting this vector here corresponding to this crop, then passing that vector onto an SVM. Like I mentioned previously, this vector here could just be the raw pixel values, the intensity values. Or they can be more high-powered features such as HOG, which we'll talk about now. And we pass them on to our SVM. And as you can imagine, the SVM here is being run over these image using sliding window approaches. Therefore, it will produce many candidate regions, which it thinks there is a person in. And then we use this post-processing step here, non-maximum suppression, to get rid of some of the overlapping detected regions. So this histogram of oriented gradients is kind of interesting, and this will be my only computer vision lesson today. It'll be a representative way of how we processed pixels in the old days. And it all revolves around gradient also, but a very simple gradient that we shall see. So first thing we're just going to talk about here is the idea of a sliding window. So as I alluded to earlier on, we would take an image like this, and then we would take a window, let's say of this size here, and then we would crop out this part of the image. And then we would take this part of the image and might pass it on to a support vector machine and say, support vector machine, is there a person, is there a face or is there a person in this part of the image? And support vector machine might say, no. Then we move on to the next, we would slide the window across maybe a couple pixels. We call that our stride. And then we look at this next crop and ask the same question. So we would keep sliding our window like this and passing this vector onto our support vector machine. And so, like I said, we could have raw pixel values here, but they don't seem to be really good in this era of object detection. So now we're going to look at histogram of oriented gradients as an approach to do some good feature engineering that can be passed on to support vector machines. So if we take an image like this, we will put a sliding window across this image here. Here's a typical sliding window here in midstream here. We take this crop, we might resize it because like we're in image processing, we're always resizing, and that might make you cringe because we might change the aspect ratio of width to height and warp things, but that's okay. We can get around it. It doesn't. It's not detrimental. So here's our crop. We might resize it to a particular size that we need. And then we could say, oh, look, I want a 64 by 128, so I'll just resize it and take those raw features. And so I'm always working in terms of these windows or crops. And so this histogram of gradients is really simple. It will look at a neighborhood of pixels. And so I'm going to have a center pixel. This is my center pixel here. And I'm going to then look at my neighbors, my 4 neighbors. So if I look at my center pixel here, I've got 8 neighbors surrounding me, but I'm just going to look at the 4 neighbors at the north, east, south, and west points of the compass here. So then I'm going to ask the question, the pixel value. So here's my pixel of interest. It's from here. And I ask the question, well, what's the value of the pixel over here? And what's the value of the pixel here? And what's the difference? That's my X gradient. So you can think of my image as a function. I've got X, Y as my spatial coordinates, and then I can think of having a third dimension coming out of the screen that gives me the intensity, or it could be RGB values as well. And I'm looking at here in terms of gray level intensity, and I say, what's the difference between this guy here and this guy here, and similarly in the Y direction I look for the difference of the gradients as well. And so then I take those values, and the first thing I'm going to do is say I'm going to this is going to give me a vector, and the vector is going to look like this. So you're all vector whizzes, so you know that I can calculate the magnitude of this vector, and I can also calculate the angle of this vector. So I'm going to take the magnitude of this vector and go to calculate the angle. And here's kind of the calculations here. And I'm going to use that. I'm going to do that calculation for all pixels in this image crop. Then I'm going to take those. So here I've done the calculations here, and I'm plotting these over here in various forms. This is the X gradient, this is the Y gradient, this is the magnitude of the gradient. And so I can visualize these things in different ways. So I'm always working, well, I tend to develop some standard practices. And so one standard practice is that I'm going to apply this calculation to all pixels in my image at the same time. And then I'm going to do these local calculations that I'm doing right now. So here is my local crop after I've calculated my HOG for each pixel. And in here, this little segment here corresponds to an 8x8 pixel arrangement. I've plotted my my gradient vectors here. So you can see that around here, I've got a lot going on. There's the person's head here. So I'm going from a very light region to a very dark region. So there's a boundary here, and this kind of there's a gradient basically. And here are the corresponding values. So I have two representations now for each pixel. I've got my gradient direction, and I also have the magnitude of the gradient. Here's the punchline. I take all these values here. This is a lot of data, so I want to summarize them. So what's a great summary of these data? It's a histogram. So I'm going to look at the gradients, and I'm going to look at the directions of the gradients. So they go from 0 to 180. And then I'm going to take the magnitudes that show up here for the different directions. So here is my gradient direction here. It's 10. And this is a complicated one. This is my direction here, 10. And so I'm going to go to the histogram here where there's 10, and then I've got a magnitude of 4 associated with that. But 10 is split between the first bucket and the second bucket, so I'll give them equal contribution from this particular pixel. So I go over all these gradient values, and I accumulate them in this histogram, and I have this 9-bucket histogram, which will summarize all this data here. Was there a question? So I've got 9 bins, so I just accumulate these. And so then one more final step, I take those histograms and I'll look at this 2x2 neighborhood in this original image, and I'll just take those. This will give me 4 histograms, 4 9-bucket histograms. I'll put them all together, and this will give me 36 values, and I'll normalize those. So it's kind of a way of smoothing, and then I'm going to represent this guy here using this 36 numbers, and I'll do the same for all these other windows here, and I end up with a vector here which is 3,780 values as I pan across this image here. So I go from this image crop here to a vector of, let's say, 4,000 values. I take that vector of 4,000 values and I pass it on to my support vector machine. So this histogram of oriented gradients hopefully makes sense right now. So it's passed on to my support vector machine. It's a very smart feature that we've engineered using computer vision background. And then we just take our sliding window approach and apply it to all areas of the image, and then we extract our hog vector, and then we classify each window. And now you can imagine how you might do this yourself in practice. So you can imagine that here is a person, and you can see their face is this size. Now here's another person, and her face is actually not this big. So I have to deal with scale. And so how do we deal with scale? We have this idea of windows, pyramid, which we'll talk about here right now. So here I've got an image. This is the original image, and I'm going to build a pyramid from the image. So all I do is I do a subsample of this image here, downsample this image to get the next size down. I divide by 2. This is 512 by 512. Then if I want to downsample this to half the size, it's 256 by 256. Then I do a quarter size. Then I do 1/8, and then 1/16. So these are all the different images as shown here. So like I said earlier, when I'm dealing with images, I like to have standard sizes, if possible, as inputs. So I'll always resize my data I'll always shoehorn my data to fit to that size. So let's say that my model expects a 32 by 32 as input. So clearly this 512 by 512 is not going to happen. I need to just take little patches of this image. So this red here corresponds to the 32 by 32 in the original image size. This blue here corresponds to this patch over here. And this yellow here corresponds to taking a patch from the 64 by 64 image. So what you can see here is my image patch or crop is 32 by 32 across all of these images. But as you can see, the lower the image is, the bigger the crop of the original image it becomes. And so this last image here, which is 32 by 32, then the sliding window has only just one operation here, application here. So this is an example of a pyramid at level 0, level 1, 2, 3, and we typically are working here in types of dividing by 2, 4, 8, 16. This is very common in image processing and also in object detection, and is still prevalent in deep learning also. So we take our image pyramid, we calculate this histogram of oriented gradients over the entire images, and then we start to window across these features here and use them to build a vector that's passed on to the support vector machine. As you can imagine, this produces a lot of possible candidate regions where maybe we found people. Then we apply non-maximum suppression, and I'll talk about that now to get down to a reasonable number of detections. So what is NMS? Well, it's a very important post-processing step, and it dates back way before deep learning approaches. And so the idea is that I want to take an image like this where I have many detections at different scales potentially, and I want to suppress some of these detections. And ultimately what I want is a bounding box for this guy here and a bounding box for this guy here. So how do I do that? It's a very simple heuristic driven algorithm, and there are maybe 1 or 2 parameters that kind of feed into it, but we'll just unpack that quickly here. So let's say that I have an image here, and I've come up with these 5 regions that I've detected where I think there are, that's in this case here, dogs. I'm going to focus on a single class here. I would do this on a per class basis. I would do NMS on a per class basis. So I would try to suppress all the dog candidate regions down to maybe 1 or a few dog regions. So each region here is depicted in color, different sizes, and then we also have probabilities associated with these regions. So how NMS works is that I am looking for the degree of overlap between candidate bounding boxes. And so typically I'll say that if a bounding box has an IOU of 0.5, that means that there will be intersection over union. It's a Jacquard measure, and if you don't know what it is, maybe look up very quickly. You'll find it rather than me having explained it right now. So there's an IOU of 0.5. If the IOU is big, if there's a big intersection over union, then clearly one region should win out, and you should drop the other one. So which one do you drop? You keep the highest probability region, and you drop all overlapping regions. So in this case here, I've got 2 regions I'm looking at here. These are the 2 highest probability. The red is the highest probability region, and then this pink seems to be there's a high degree of overlap. And as such, I'm going to suppress this pink, and I'll get this this guy here. So I keep this guy. I looked for other overlapping regions, but there are no other high overlapping regions, so this guy stays put. So then I move on to the next highest probability region, which I believe is this yellow guy here, and then I start to look for regions that have a high degree of overlap with that region. So you can imagine that I'm going to drop this purple one and this blue one as well, because they overlap to a high degree with the yellow, and the yellow has the highest probability associated for a dog, and so we keep that. So we end up downstream here with this kind of result here. So this is a very important post-processing step that we still use in deep learning as well. And so now you got the impression here that we're taking images, we slide a window across these images, we extract various crops, we might have to resize, then we pass them on to a support vector machine, we get many candidates, then we suppress, and we get our output result. And this was state-of-the-art circa 2005, and then there were little evolutions of this approach, this pipeline, that kind of over the next 5 to say years or so. And so just to kind of give you a comparison here, this type of approach would give us about I think 12% average precision on just the person class here in 2005. So it's a pretty low performer given all the mean average precision curves I showed you earlier. Okay, so I have a notebook for this, and I guess I won't go into details here because we're kind of low on time, but I encourage you to kind of reach out there and look at that notebook, because you know what, it's a really cool notebook. Not because I put it together or anything like that, but it's actually really, it kind of helps you walk through some of what I just talked about. Because sometimes if you don't get in there and load an image, if you don't window over the image, if you don't build this histogram of oriented features from scratch or use call a library, you know, so implementing this 5-step pipeline is really highly instructive, I think, if you're a novice to this area, and of course if you've got lots of time. So here is one way in which you could build out that pipeline. Here's kind of the main steps here. So here I'm going to build a face detector, and in the notebook you'll see that as well, that I build a face detector. And what I do is I download a sample, a database of face images. There are multiple databases out there, and then I warp all the images to be the same size, just because we can do it, I guess, and it doesn't adversely affect things too much. And then I also have a bunch, this is all positive data here. So I'm trying to build an SVM classifier, essentially, that will say, is there an image, or is there a person, is there a face in this image crop or not? And then I'm going to try to find some negative examples. And this is a classic way of finding or generating negative examples. So I'm going to take a whole bunch of images, and I'm going to assume there's no persons in those images. And I again look at scikit image, and there are some images that are built in. And I think I look at maybe 10 or 20 images from scikit image, and I generate a whole bunch of negative examples based upon cropping or patching subparts of the image. And I combine the positive and negative examples, and I train a support vector machine. Sometimes this works really well, but sometimes I'm finding that my negative examples are too easy, and therefore I can do a great job, but really if I put out there in practice, it won't do a great job. So I do some hard negative mining, meaning that I look for some false positives from my trained SVM here, and I try to select those examples over the easy examples. I try to get rid of easy examples and focus on the difficult examples. And so this is hard negative mining, and we still use that kind of practice also in object detection. So I will do this once, maybe multiple times, so that I can get to use good positive negative examples, and then I have my suppression step, my NMS step for and so as I said, this is my image pyramid, and you'll find in the notebook there's all this code for just running around the images and doing stuff on images. And here is my detector, and so I've ran my support vector machine classifier that's the detecting faces at different levels in this image hierarchy, and you can see there's different sizes of boxes here, bounding boxes, and so here's all the detections at a certain level of probability. And I had to also add a post-processing step to my support vector machine to get probabilities out of that. And then I apply NMS to these detections, and I end up getting these regions here using my very cheap face detector. So you'll not be impressed, I guess. This is not bad. This is false positive, but anyway, I leave some exercises in the notebook also for you to kind of try out. And so really, we need to be here. This is what we need to be doing here. And so modern day face detection systems they're amazing. And there's I think FaceNet, or it's a whole bunch of them that just will not just find the faces, but the eyes and the lips and noses and other key points and so on. So go play with this notebook when you get a chance, maybe over the break here. And as I mentioned, this is a great training exercise. It brings together a lot of the components that we'll use later in deep learning. Now, we're going to keep going for another maybe 10 minutes or so, and then we're going to break if people feel they need to have a break. And maybe Penyang, maybe you can open the chat there to see if people want to have a break, and close it afterwards. So Yes, so deep learning. So in the old days, we were, I guess we were spoiled because our loss functions were very simple. They just had a data loss component where maybe we had a mean squared error loss. And then we started to introduce complications like regularization terms and so on. And so with the advent of deep learning, we're getting even more ambitious. We're kind of having these multitask loss functions. And so these are really important in object detection. And I think that it's something that we don't do every day. So I'll just call it out explicitly very briefly. So when it comes to machine learning, we have this typical pipeline that we follow, but when it comes to deep learning, we spend a lot of time on architectures and loss functions. And you'll appreciate that even more so by the end of today's presentation. And so our architectures are really amazing. And I don't know if you've ever coded up an architecture from scratch, but you can wire your network as you like. You can connect any layer to any layer as you like. And it might be just totally circular gibberish. And these deep learning frameworks like PyTorch, TensorFlow, Keras, all those guys, they will all try to learn something for you. They will say, okay, great job. I'll compute a gradient and I'll just help you out. So we have to be careful with this power, but it's extremely flexible, and our loss functions are also flexible. But in the old days, if we wanted to learn a machine learning model like a linear regression model, we might say this is our loss function, this is our mean squared error loss function, and then we might compute the gradient, get our normal equation. We might then say, look, give us the gradients of this loss function, and let's do gradient descent. And this might be my gradient descent iteration step here. And then we might say, okay, let's go take this math-based equation and let's write some code. And so here I'm doing some tensor programming or NumPy programming. And so I can take my equation here and pretty much represent this out here as a line of code. And that's great. But as you all well know, when you start to do things like this, you make mistakes. You make small mistakes that can take days to debug, and it can be very painful and tedious. This is a very simple loss function here. And in Keras, we can specify these loss functions just by specifying the architecture. So here's my input, and here's my output. And then I can have a model in Keras where I combine my inputs and my outputs. And then I can say, I want a mean squared error and do some gradient descent. And, oh, by the way, track some other metrics as well. And then I can go take my model and go fit it with various data sets. And so basically here, all I got to do is say, specify the architecture and specify the loss function and tell which flavor of gradient descent you want to use. And the rest is taken care of automatically. So this old way of writing machine learning algorithms is very tedious and error prone. The new way is very high level, and this is Keras, and we'll see later that in PyTorch it's a little bit simpler. It's a bit more natural in terms of tensor programming. So anyway, so the bottom line is we need to be able to deal with more complicated loss functions. This is a really complicated loss function at first sight, but once you start to unpack it, we'll see that it's not that bad at all. We'll unpack it later, but we need to be able to deal with this. So just to get our head around multitask loss functions here, we're going to look at this MNIST problem. Previously, we would just classify this digit here as 1. It's a classification problem. I'm going to change the problem here to say, I'm going to make it a multitask problem where I want to not only predict the class, but I also want to predict the percentage of, say, of dark pixels in each image. And so there's no reason why I'm doing this apart from just being pedagogical. So now I've got this two-pronged loss function that I need to optimize, class and a regression problem where the percentage of dark pixels. So I can create this data set very quickly, easily, as you can imagine. And this is how I would solve it. This is how it solved the classification problem here. This is my input digit. And this is my convolutional layers. I might flatten and then have a dense output layer to give me 10 class values for the 10 digits of interest. And so what I'm going to do now is add an extra head here, which says I'm going to predict the percentage of dark pixels. So this is just a blown up version of that. And now the question is, how can I do this? In Keras, it's pretty straightforward. In PyTorch, it's even simpler. And so the goal here is that we've got these, this is our network architecture. And then we need to have a loss associated with each of these heads. So we have a cross entropy loss here. We've got a mean squared error loss here, L2 or L1, depending on what we want to do. And then we just combine these two losses. So how do we do that in Keras? I'm just whizzing through this stuff here. You can try to understand how we build. So this is our convolutional network here. We give it our input. We add convolutional layers. We then have max pooling, we flatten, and then we take the output of this flattened layer and we pass it on to two heads. So we have this fully connected layer for classification. Now we've got a classification head here that culminates in a dense layer of 10 neurons, and we got a regression head here with one dense neuron in the output layer. And then we build our model here. We've got a single input as our image, and we got multiple output heads here. We've got the out classification and out regression. Then we want to, so we've got our model, and then we want to compile the model, and we say that we want to have what losses we want to associated with each head. So we've got a categorical loss associated with the classification head. We've got an MSE associated with the regression head. We combine those two loss components equally, 0.5, 0.5, and then we track metrics for the classification head, which is, this is the regression head. Here's named regression head. This is named classification head, and we can associate with these heads different metrics that we want to track during training. This is another visual of our network, and you can see that this is our backbone network here, and then we branch out into our classification and our regression heads. And regularization is already kind of natural part of the process here. So we don't have to worry about that. So this is a notebook that you have access to as well. And so you should go play with that notebook and maybe think about other crazy problems you can do with an MNIST to flex your muscle around multitask objective functions. So essentially, this is when you know, fitting this model is like just fitting a regular old model, and we just send a batch of data, how many epochs we want, do we want validation set, then we have callbacks that call TensorBoard, and then we also have this checkpoint where we want to say save the model every so often, in this case every epoch. And here's our, we can then separate out the different metrics that we're interested in, and we can launch TensorBoard, and we can track these things all pretty easily. So the bottom line here is that this is just an example of how we can do multitask deal with multitask objective functions. And I encourage you to take your time and look at this. And these functions are, loss functions are being used a lot these days for simple problems like style transfer and more complicated problems such as object detection and beyond. Okay, so I'm going to pose a problem here before we go to break, and then you can noodle on this problem over the break, and maybe you come back and say, hey, I've reinvented the future. So the problem is that we saw that sliding windows is a really useful technique for panning across an image to find local instances of objects of interest. We also saw that image pyramids was a great way of finding objects at different levels of resolution. Now, those are all super expensive operations. And so when it comes to coding, if you see a for loop in a program, it's almost as bad as seeing a go-to statement. If you recall what a go-to statement is. So for loops are notoriously slow, and they're not amenable to parallelization. Whereas if we can do things in vectors or matrices or tensors, then we can highly parallelize these things in our GPUs and so on. And so the goal here is, how do we go from these for loops This is one for loop. This is another for loop here. How do we go from 2 for loops here into a deep learning architecture that's super efficient and effective? And we're going to look at sliding windows first. So here, so we have a task, and our task is, and this is going to just kind of motivate us and kind of ground us a little bit. And so now we've figured out how to classify digits, and so that's easy. So next up, I want to change the task again and say I want to classify the digit, but I also want you to tell me the bounding box that bounds that digit. So here we got a figure 8. Down here, I'm saying, tell me exactly where is that figure 8 in the image. Give me the top left-hand corner and give me the height and width of the bounding box that contains that digit. And so you can imagine that we can very easily create this data set by ourselves. And so now my problem is to predict what is the class and give me the bounding box information as well. So it's a multitask loss function. So that's all well and good. I think we can figure out how to do that. We've got our classification head as usual, and then our bounding box here. Now we have 4 values that we're trying to predict. The X and Y of the top left-hand corner, and maybe the width and height, if that's the way we encode the bounding box. So we just kind of made our loss function a little bit more complicated, but it shouldn't phase us too much. So, and we could even add a third component here as well if you need it. So then we could just work on a simple problem here where we say, let's look at the number 8 versus the rest of the digit world and just have a binary classifier and still do the same thing. So then we might make things a little bit easier or more complicated in saying, look, why don't we not just have a digit in the center of the image here? Why don't we just put digits anywhere in the image and try to detect what is the digit and where is it located in the image? So that's kind of a new problem here. So it's kind of digit classifier and localizer for non-centered digit data. So how can we do that? And so we could try to solve it using our existing stack here, but I think we would run into problems because the scale of the digit here has changed quite a bit. So we've got small digits, big digits, top left, top right, they're all over the place. So this is kind of like maybe a typical data set here where the digits tend to be scattered. So one approach here is to generate lots of data here. We could just generate artificial examples, lots of them, and hope that our classifier and our detector would work well. And so we could try that, but probably won't work that well. Another approach here is that we could take our sliding window approach that we've learned already at different scales, and we could kind of have this kind of extract patches and take our trained up classifier, digit classifier that from MNIST, and basically we would extract windows from these, or crops from these images. We would right size them and say, hey, let's say that MNIST is 28 by 28. That's what it expects to classify digits. So then we would take all the sliding windows approach and extract crops of that size and scales and apply this approach. And then that could work well. But again, that's 2 for loops because we got the for loop over the sliding window over the image, and then we got the for loop for the scales as well. So that's pretty much not what we want. And then the third approach here is the convolutional approach, which I just talked about as a problem. So we can see that this is our windowing across, and then we can write for loops and do a kind of a brute force kind of search across those. And that works well to a certain level, but it's not efficient. And so I'm going to pose the problem is, how do we take this, first of all, how do we take this sliding window approach, that for loop associated with that, and how do we replace that with a single convolutional layer? And I'll just kind of want you to keep in mind here that this is our image here. And we've got pixels, like say 400 by 400, and we got a depth of 3 because we got RGB. And over here, I've got a feature map spatially expressed as 4 by 4 by 1. And so the question is, how do I go from here to here? And then let's say I just have a single feature map here. So how would I do that in under a regular deep neural network layer? So the answer is I can do a convolutional layer 100 by 100 with a stride of 100, and this will certainly give me this. There are many ways I can do this, but this is a simple one. And then if I want more depth, I can have 64 of those if I want 64, a depth of 64. So now the idea here is that I have a cell here in my output feature map, and there's a relationship between this cell and the image. This value here is the result of applying a 100 by 100 kernel. This kernel is applied to a 100 by 100 patch here in the image. This is these are let's call them input variables, 100 by 100. So it's 10,000 input variables here, and they all have something to do with this value here. And so as such, we call this cell here, this cell's receptive field in the input feature in the input image here is this patch here, this blue patch here. So we call this blue patch the receptive field corresponding to this cell in the output feature map here. And this idea of receptive field and this relationship between this cell value here and this input image pixels here is really critical when it comes to object detection. We're going to use this notion quite a bit, and this will also help us how to take these for loops out of the business here altogether. So and so in addition, and sometimes this works really well, is that if I have such a nice feature map here, I can compute this value here independently of this value here, of this value. So this is a highly parallelizable task here. So each of these cell values here can be calculated in parallel. And so we call this a fully convolutional neural network in some ways. And so it's FCN, and we'll use that word FCN over and over. And as such, these are highly parallelizable. And so in the early days of computer vision, we were looking for everything we could do to speed up the processing. So we could totally take a convolution operation like this, and we could divide it into all these little sub-problems. And so it's a divide and conquer problem to big problems. And so this idea of this cell here mapping onto a receptive field here is going to be exploited in many different ways today. And one of these exploits will be in terms of getting the sliding window approach down. So I think we're going to stop for a break maybe here for, let's say, can we do a 5-minute bio break? Would that be okay? Maybe stretch your legs. And again, maybe you can switch on the chat now, Pinyang, just if people might have questions or.
Yeah, some people just ask for the link of the slides.
So the slides will be made available later this week in the next, say, 2 to 3 days.
Okay, sure. Yeah.
Okay, great. And of course, yeah, you can send, if you send messages, I'll get them here. Pinyang and I will get them privately. It won't be for everybody. So I assume that you want a break. So it is now, let's call it 2:45, 2:50, we resume. Is that okay? Okay, so then I assume radio silence means that we'll see each other at 2:50 West Coast time. I'm sure we have people from all over the world here, but 2:50 is kind of where it's at. Okay, I can appreciate that maybe people needed a couple extra minutes here. So Sasha, you have a question, and would you mind just maybe articulating the question by using your mic?
Yeah, James, thank you very much. Really appreciate the tutorial. Really learned a ton. So what I'm thinking about is this. It seems like a lot of the approaches we have for image analysis, object detection, are kind of bottom up. They start from the pixels and they create these kernels, and then we have all the pre-processing. On the other hand, I think that probably the human brain looks at this problem differently. I mean, I think we have some kind of a built-in preconceived notions like, oh, I'm looking for a cat in this room, and so we kind of we know that the cat might be hiding behind the sofa. So we might the brain probably operates with some kind of knowledge ontologies about the kind of things that might happen with an image, and
Sure.
yeah. So how is it possible to somehow program it in or create structures that somehow include that information and knowledge?
Sure. So it's a really great question, and so we'll see that we're going to maybe look very briefly at some more bottom-up approaches where we say work from the pixels up. So we might think of taking those pixels, clustering them somehow based upon RGB values and spatial relationships and so on. And so that's bottom up. You'll see shortly that we'll have top-down approaches, but they're top-down in the sense that we have explicit bias associated with what we want to do. We say, okay, we'll actually impose a structure that says, hey, we're going to partition our image into zones, into those windows. So you can think of that windowing as kind of a top-down approach to organizing our data. And so then the part about your knowledge, how do we take knowledge? And actually, at this point, actually, I figured out we can turn on the cameras. So if you wouldn't mind switching on your cameras, it would be nice to have some visual company on the journey here today. So if that's okay with you guys, that would be much appreciated. So back to how do we incorporate knowledge into this world? So there've been a number of attempts to incorporate knowledge. So far we've had one brave camper here, Sasha. Thank you so much for stepping out and turning on the camera. Others, please get dressed and switch on your cameras, please. This is a tutorial after all. So last year or 2 years ago at CVPR, there was an interesting piece of work where we're working on object detection. And this is not my paper, it's somebody else that was kind of clever. And basically, look at COCO. You see 80 classes, so 80. So that means that some of the classes have a world relationship. So it could be person, there could be a cyclist, there could be a jogger, there could be a car, bicycle. So there's some relationships there between those objects. So can you take that knowledge, that kind of ontology of information, and bring it to bear in some of the tasks that might come up in these pipelines? And so somebody, I think from Japan, did a really great job. I think it was from the Chainer group in Japan. He took this idea of an ontology and used that in negative mining, I believe. And so when we train things here, we're always looking for maybe positive and negative examples of objects. And I think he chose negative examples based upon the ontology. So maybe examples that are in the same subtree, maybe difficult to separate, maybe, and you might want to give those higher probability of selection. So I forget exactly how he incorporated this knowledge, but at the time I remember thinking that that was a really clever idea of using domain knowledge. So otherwise, we'll see that this is we're on a path of brute force here in terms of tensors and tensor programming and deep learning. And background knowledge makes its way in at certain points when we're faced with computational overload. So we see that the windowing approach that we saw here earlier, that's one way to deal with, to address the problem. So we divide and conquer that problem in a particular way to solve it. So it's a top-down, we're taking knowledge and trying to help out the system. And so, so far, in this object detection from a deep learning perspective, we've been taking old ideas and trying to operationalize them within deep learning pipelines. But the DETR, the transformer approach, that is very, very cool, I would say revolutionary idea. And getting knowledge into that world, I'm not sure how that can be done that easily. But so, all right, so that helps, Sasha?
Yeah, thank you.
Great. And so do we have any other brave souls in terms of switching on the cameras? It would be nice to have some visual company. Are all the cameras broken? I can only see myself, and I can see Sasha, and I can see Sam. Welcome, Sam. Thank you. And so, all right, so let's resume. And I'm just going to very briefly go through this, and then I'm going to skip ahead and look at other things. So, so before the break, we said, you know, is there, the problem was, is there a way for us to replace this for loops, this windowing over the image here as a for loop? Can we do that in a faster way in a convolutional neural network? And that's an age-old problem. And so the answer is yes, and I'm going to show you why. And then also, can we take this pyramidal approach where we had images of different resolution? Can we also do something smart there? So, so basically, we saw how a convolutional kernel can be applied. We can divide and conquer this whole computation here by computing each cell value here independent of the others, and so on. And we can also do this for intermediate layers. So we can trace all the way back. We can trace the lineage of this pixel here, this value here, this cell value here, all the way back to this layer, back to this input image as well. And so you can work it out. I won't pause to kind of for you to calculate that, but you can do that. And so then, what we have here is the idea of a receptive field, saying that this cell value here is dependent upon these guys here and ultimately these guys here. And that's a big moment. So then that allows us to tie back this cell here. This tie back to the input is kind of important in object detection, because what we can do then is say, oh, we're interested in this object here. This object here occurs. So I have this feature map here. It's a 4x4 grid here spatially. I've overlaid that 4x4 grid here, saying, look, each of these grids here, or pixels, has a corresponding cell here in the output feature map. So then if I find an object that's in this cell here, I can say that this object here is tied to this value here, this cell value here. Do you, is that reasonable to you? Does that sound okay? This little tie, this kind of tying the output, let's call this an output feature map here. And so this gives us a way of connecting labels or ground truth data to input regions. Because as a human labeler, I will draw a box around this dog here and say, there's a dog here. This is the bounding box for this dog. So how can I take that information and tie it to some sort of target value? Well, I could say that this dog is primarily in this cell here, or in this region here, and that this region here corresponds to this output cell here. So I should focus all my attention to find the dog here in this cell output feature map cell value here. So that's kind of something to keep in the back of your mind for the moment, but that's kind of connecting the output values of a feature map with our input regions. And these are called the receptive fields. So here I've got 16 receptive fields, that one for each of the cell values in our feature map here. So then, so one more thing. So here's our typical classic convolutional neural network for doing classification that you have probably built many of. Here's our input image. We pass it through various convolutional layers, get all these feature maps and downsampled feature maps. Then we flatten things out, fully connected layer, fully connected layer, fully connected layer, and then we might do classification in the case of MNIST. So this is a kind of a hybrid network. And a hybrid network, it breaks our idea of parallelization. So previously I talked about parallelization where each of these little cells here can be computed independently of the other. And that's a nice little parallelization trick I can embrace. So then this architecture here breaks that. So the question is, how do I go from a hybrid architecture here to a fully convolutional architecture here? And this is kind of a key slide here. And so here's my convolutional network here. Well, I can very easily translate this fully connected layer here, which there are 400 values here, 400 neurons here. I can convert that into a 1-by-1 a feature map here with 400 values in depth. So how do I do that? I go from this feature map here, which is 5x5 by 16. I apply a 5x5 kernel. I apply 400 of those, and I get down to this 1-by-1 by 400. So this vector here has a very similar relationship to this vector here. They're pretty much very similar, maybe even the same in this case here. So I've shown how I can replace a fully connected layer here with a convolutional layer here. So far to here, my network is now fully convolutional. Similarly, I can replace this layer here with another convolutional layer. Again, I will use 1-by-1 kernels, and I'll use 400 of them so I can have the same number of neurons. And similarly, I can downsample this guy here to 10 output values because that's the number of neurons in my output layer here. And I take a 1-by-1 and a kernel, and I apply 10 of those, and I get my output feature map. My output feature map is a 1-by-1 spatially with a depth of 10. So those 10 values there are my 10 probabilities that I can use to predict the 10 digits in my, let's say, MNIST problem. So does that make sense? So this is a hybrid network here. This is a fully convolutional neural network here. And that's an important concept. So then, I can, let's say my input is this 14-by-14. So if I apply my neural network to this 14-by-14 field here, and I pass that, let's say, receptive field through my network here, I end up getting out this vector 1-by-1 by 10. Nothing new there. So now if I slide my receptive field, my input along here, let's use the kind of sliding window type of approach, let's say. I slide it on with a stride of 2. I take a different crop of my input image, and I apply that. I end up getting another vector in my output space. And spatially speaking, these vectors are side by side. I can also take another crop of the input image and another crop, and I end up getting this 2-by-2 space here. So in essence, what I've done here is I've done a sliding window of my input space here, and I've ended up with a feature map space that is 2-by-2. And I can see the relationship between this this cell value here and the input space here. So this red area here is my receptive field for this cell in my output feature map. Similarly, I can say the same for the other cell values here. This guy here maps onto this guy here. So essentially what I've done here is I've said this sliding window approach is kind of like a convolution, an extra convolutional layer. So I could have realized this here by using for loops, using a sliding window for loops, take those crops, give them to a neural network, and reproduce this kind of feature map here. Alternatively, how can I replace this with a for loop? Any ideas? You can feel free to send an amazing text on the chat here if you want. So all I need to do is add a convolutional layer to my input image. In this case here, saying my kernel size is 14 by 14, stride 2 by 2, no padding, and I will get the same output here. So what I did previously was I use a sliding window with a for loop. Here I'm using a convolutional layer to realize the same outcome. So when I use a convolutional layer instead of a for loop, this is so much faster, so much more efficient, because I'm sharing computations across the stack here. So it's much more efficient, and as I say, sometimes you can actually benefit from it's highly parallelizable as well. So this idea of fully convolutional neural network is really important and has many applications. So here's my input image, pass it through a convolutional layer after convolutional layer, and I end up getting this output feature map here, which is as a result of a convolutional layer application. So this is fully convolutional. There's no dense layer here, no fully connected layers, and so it's super attractive because I got 4 sub-problems here that I can solve in parallel if I wanted to. And there's no for loops for sliding windows over things. It's all realized using a convolutional layer. In addition, I can use this idea of, here's an input image here. And let's say I wanted to label each image or each pixel in this image. Then I can pass it through a convolutional layer, and then I can upsample my convolutional feature maps here to get a value for each pixel in the output layer here. So this is a second use of a fully convolutional layer, and this is what happens when we do image segmentation. Okay, so we've kind of replaced for loops for the sliding windows. So I hope I've convinced you and shown you how you can do that. Catherine, do you feel you're okay with that now? Or were you always okay with that? All right, good. So next task is, well, how do I train such a network like this? Now I've changed the problem because I have different parts of my input that I'm working with. So I need to change up my labeling process. And so here's my image here. And let's say that I artificially created a grid here of 2 by 2, which corresponds to my 2 by 2 output feature map. So each cell in my output feature map here corresponds to all these pixels here in this quadrant here. So I've got four cells in my output feature map, and they map onto 4 receptive fields here, 4 quadrants. In this case, I've artificially done this. So so that works well. So basically what I'm saying is that this quadrant, this cell here, maps onto this quadrant here. So if I have a class in here like 8, then how do I get this cell here to tell me if there's an 8 here or not, or a 9 or a 0 or nothing even? So how do I do that? Well, I'm going to do what I did previously. And in addition, I'm going to produce my 2 by 2 output space here. And I'm going to produce 10 numbers for each cell value here. 1 value for each of those 10 classes. And so this will enable me to do classification in each of these quadrants. And so to label these things, then I'm going to have to provide vectors for each quadrant. And this is extra homework I have to do in order to build this type of classifier, but this is kind of the stuff we do in object detection. So essentially for each quadrant here, I'm going to have a target vector that says, is there an object present? And then I'm going to one-hot encode the category if there is an object present. So this is the object present, and then in this case here, oh, it's the number 8. And I'm going to create such vectors for each of these quadrants that will correspond to a cell in my output feature map. And I'm then going to have to change my loss function as well, because now my loss function has quadrupled because I've got 4 target cell vectors. And as you can imagine, I can just have a cross entropy loss for the category here, and I might have a binary cross entropy for this object present or not. And if an object is present, I'm going to do the loss on the categories. If the object is not present, then I'm not going to worry about that. So so this idea of input image and corresponding output feature map is key to object detection. It connects our abstract output space with our input pixels here via these receptive fields. And we'll use this to great avail because we're going to tie these cells here to ground truth values. And this is kind of what we do in a lot of these image object detection pipelines. So this is our input image here. We see that we've got a motorcycle here, we got a person here. Typically, we're going to have a bounding box around the objects of interest. We're going to humanly label these. And then we're going to have maybe a center of this bounding box. So this person center might be here. And then the motorbike might be here. And here and it doesn't correspond naturally to the center, but what we've done here is we said, our output feature map here is going to be a 7x7 grid. And then we overlay this output feature map 7x7 grid on this input image here. You can see these faint gray lines. And then we see that the center of the motorcycle kind of falls into this cell, this receptive field here, which corresponds to this cell in the output feature map. So each cell in the output feature map is associated with a target vector. The target vector has the X, Y, Z, so X, Y, and the width and height of our objects that might be in that input receptive field. And we also have the category of object associated with it as well. And we might have a probability saying, is there an object in here too? What's the objectiveness? Is there objectness of this cell? Is there an object in this cell value which has a feature, it has a receptive field here? So that gives us a way to connect the ground truth to our output feature maps. And as you can see, the object here is not fully contained in this receptive field. So this guy here so this motorbike here this is the bounding box for motorbike. And maybe the more natural center of gravity might be here. But so this kind of grid over here, this is our output feature map here. This guy here is very crude. It's very pixelated and so this is the center of this region here, which might correspond to this center in the receptive field. So we can see there's a gap here between the center of the receptive field and the actual center of the object. So that little gap there is kind of what we're going to predict. We're going to say, how far off is the center of the object from this center? So that'll be my XY offset. In addition, I'll see that my receptive field is this guy here, but my bounding box is much bigger. So my width and height will have to kind of deal with that. So this type of encoding is really prevalent in object detection. And so we have this kind of XY offsets, and then we have width and height also as expressed here. And normally we'll try to normalize these values So we'll normalize the offsets, the XY offsets, and we'll also normalize the width and height maybe by the width of the image. So the image width, and we'll normalize the height by the image height. We'll just divide it by the image height. There might be other types of normalizations we'll do as well, but just for simplicity. So this is how we would encode our ground truth and tie it to our output layer in our network. So then you can imagine that we can do cross entropy with the classes here. We got 4 classes that we're interested here, for example, and then we could do kind of a mean squared error difference between the X, Y, W, H values here. So we can have our multitask loss function, mean squared error plus cross entropy, and away we go. So we have, in this case here, we've got 7 by 7 feature map. And that means we've got 49 values or cells in this feature map. And let's say in this case here, we only have 4 classes, and then we have this objectness probability as well. Is there an object in this cell or not? Then that corresponds to 9 values. So we got 9 values for each of these 7 by 7 grid here. So our output layer will be predicting 7 by 7 by 49. I said by 9. I'm sorry. Whatever that's a vector that's let's say 400 or 500 long vector. So these vectors here. So I'm sorry. This is the tensor here. This is for one image, and so we've got 7 by 7 by 9. So that means that we are going to predict about 445, let's say, values. So there's 445 values that we have to predict here. And in this case here, everything is kind of zeros apart from this guy here and this guy here. And so now your NumPy programming, your tensor programming will come into real good to avail here, because we have to kind of be able to extract the object cells and the no object cells. So this is an object cell here, and this is an object cell here. All the other guys are no object cells. And we need to be able to work with the object and no object cells. And so our loss function becomes so much more complicated. But it's not too bad once you get your head around tensor programming. So, all right, so I'm going to move on here, and we're going to talk just pyramids is kind of not too difficult. It's a very clever idea that to kind of, so how do we take this pyramid thing, and there's a for loop here. Let's say we got three levels in our pyramid here, so we got a for loop that's going to iterate 3 times here. So how do we eliminate that using a deep learning architecture? So here's our sliding window here. Here's our sliding window at a different level of granularity. And this is the original scale. This is 50% of the original scale. So this guy is back in 2014. Jan LeCun and a bunch of other folks here, Rob Ferguson, all, they introduced overfeed as a way to do an integrated windowing plus feature pyramid into a convolutional neural network architecture. So here's our image here. The classic approach would be to kind of have a window, and now we know how to do the windowing. We do a convolutional layer, and we come out with a bunch of vectors here that are feature maps that we might pass on to the classification head and regression head. And we know now how to make these things fully convolutional for classification head and regression head. And so then the big moment here is that we take an image like this. This is the original image here. We pass it through our convolutional layer, and our convolutional neural network, and we get an output feature map like this. That's 2 by 3. And in each of those cells here in 2 by 3, we're saying, is there, I'm sorry, this is the original, sorry, this is the original scale. 245 by 245, and we give it to our object detector. Our object detector has a multitask. It has saying, is there an object, and what is the size of the bounding box for that object? So we take our image, we pass it through our detector, our convolutional neural network, and we get a single cell in our output feature map. It's a 1 by 1 feature map, and it's going to have a depth here of corresponding to the number of classes that we have, and maybe a bounding box. So we say each network is capable of predicting a class and a bounding box. So if you've got 20 classes, then we got 20 values here that we want to have for classes. And then we have a bounding box. We're going to have X, Y, width and height, and maybe also an objectness probability as well. So this is all pretty straightforward. We kind of know how to do this very easily. So now, if I take a bigger image, if I scale up my image, now I can convolve this image like we saw previously, and I get a new output feature map. It's got a different scale here, resolution. And as you can see, I can keep taking my image pyramid here, and I will get different size output feature maps. And each output feature map will be giving me predictions. So in some ways, each of these cells here is like an image patch, where we ask the question, is there an object there? If so, what's the class of the object? And can you give me the dimensions of the bounding box for that image? So as you can see, the bounding box doesn't sometimes, so this is the bounding box here for this guy here. Or sorry, not bounding box, this is the image patch. 245 by 245 that we will first of all pass to our network. And as you can see, this person here is not entirely contained within that. So our kind of matching between these receptive fields and our output feature maps is not perfect, and we're asking a lot of our network to predict tall objects and skinny objects and wide objects, and so we want to kind of think about that and how we can deal with that. So this is a multi-scale object detector, and we just we pass those into our network. So this is basically overfit in practice, and we are taking our images at different scales and passing them through our network, and then we end up getting different feature maps. So essentially what we're doing here is we are taking image crops or patches, and then we're classifying them in an efficient way. And that's all that's happening here. But doing that becomes really efficient, and also it led to some great results. So, but this overfit was kind of it was a kind of a breakthrough moment of sorts back in 2014, and it left a lot on the table. So as you can imagine, the overfit here, it's kind of this network here is optimized on patches. I take a patch from an image, and then I optimize whether there's an object there and what's the bounding box and so on for that object and so on. So it's very much a local optimization problem. But it doesn't take into account that this patch here is part of an image where there's other patches, and it's not global. So that's one of the limitations of this approach. And so we'll see how we can maybe address that limitation subsequently. Of course, we still apply our non-maximum suppression approach to this, and so this idea of image pyramids and windowing is really important, and we'll see it. It's definitely part of overfeed, and we'll see it also come up here in other approaches as well. So in terms of deep learning approaches to object detection, we're going to beg, borrow, and steal things from all of what we talked about so far. And we're going to come up with two-stage approaches, one-stage approaches, and then we have this new wave. Two-stage approaches are basically, we take our image, pass it through a convolutional backbone system here. It could be AlexNet, it could be VGG16. We get our output feature map, and then we pass that output feature map through a proposal generator. And then so this is one stage here, proposal generator. I'll tell you about that in a moment. And then we take those proposals and then we classify them and detect. And so this is stage one, this is stage two. And whereas our one stage model says, hey, just take the image and go straight through in one pass and give me the objects, classes, and the bounding boxes. So this is a two-step process here. We're going to talk about it very briefly. And here is kind of a network architecture. This is our input image, pass it through some convolutional neural network like VGG16. And then we go here to find out regions in the image that have objects. And then once we know there's objects in the image in that region, then we pass them down here. And this is in contrast to one-step approaches where we take our input image here and we just pass it through convolutional layer, convolutional layer, convolutional layer, and then we get our output here. And we'll talk more about these arcs here momentarily, and then we apply non-maximum suppression. We also apply non-maximum suppression here as well. Here and also here as well, actually, as it turns out. We'll talk about that in a moment. So just to give you a sense of where we're at right now, we've moved into the deep learning phase, and we're going to look at three families here. These are our two-step approaches here in the dotted lines, and then there's the solid boxes here, which correspond to one-stage approaches. These are also one-stage approaches, but they're special. We'll talk about them. So I'm going to talk just briefly about this two-stage approach. I'm going to give you an example, and then we're going to talk about this two-stage approach. We're going to look at some code briefly, and then we're going to talk about this new wave. So RCNN is it's a region-based convolutional neural network. It was introduced back in 2014, CVPR 2014. Computer vision pattern recognition is a big conference it's twice the size of KDD in terms of participants. And region-based convolutional neural networks, the idea is very simple. We take an image here, and we have bounding boxes associated with things where the ground truth is associated with bounding boxes. This is a blue box here, is a person, and then we have our first step says, hey, let me find areas in the image where there might be objects. And we call these region proposals. So we're proposing that maybe there's a person here. This is all red here right now. I apologize for all the red. And then I have maybe other regions also. So I find a bunch of regions here, candidate regions where I think there are objects. Then I take that candidate region and I warp it. So if you recall, AlexNet is, what's the input for AlexNet? It's 224 by 224. So clearly this region here is not 224 by 24. So I just warp it. I force it to be 224 by 224. So hence I'm just totally out of whack here. So I take that warped proposal and I pass it through a convolutional neural network like AlexNet. I take the flattened vector of values from AlexNet and I pass them on to a support vector machine. And I say, support vector machine, is this a person or not? And then I also say, oh, tell me, give me the coordinates of this bounding box. And so I end up predicting this bounding box here. I say, here's my top left corner, and here's my bottom right based upon width and height. And as you can see, my prediction here, the dashed line here, overlaps with the true positive. So there's a high degree of overlap. The IOU is pretty high. So I might say, good job, that's a true positive. I also predicted this guy over here. That's a false positive. So as I mentioned, the idea here is find candidate regions and just classify them. That's the idea behind RCNN. And so we take our input image, we generate these region proposals, and then we pass them through AlexNet, and we warp them. We warp them to get this output, to give them as input to AlexNet. And this is AlexNet here, and AlexNet is very strict to say, I want 224 by 224, so I have to upsample or downsample, whatever I need to do these region proposals. And then I do an SVM classification using the output vector of my my dense layers in the AlexNet backbone. I use a SVM classifier. I also use ridge regression for to predict the coordinates. And so how do I generate these region proposals? I could just have a simple clustering algorithm. And so I would cluster based upon color maybe, or texture and other things. And here you can see that I've got all these small clusters here. Then I might say, let's grow the cluster, let's consolidate these clusters. So I get bigger clusters, and then I get down to a few clusters. So you can see I've got a little hierarchy going here. And I might take each of these clusters here and pass them on to my AlexNet and then do the warping. So I right size everything. So I end up normally generating 2,000 proposals or more per image that have to be passed through AlexNet to generate this feature vector, and then it'd be classified and regressed over. And this is really a very time-consuming process. So just to be quick here, this is our training data. We extract a whole bunch of region proposals using our clustering algorithm. And of course, we've pre-trained AlexNet as well. And so we're going to do transfer learning there. So then we take those region proposals and we classify them as objects. So we warp them, I'm sorry, we warp them. And some of the regions will correspond to objects naturally, and some will be non-objects. Then we pass them through AlexNet, and that gives us a feature vector. And then we can take those feature vectors and build an SVM classifier for each class of interest. And we can also build a regression model as well to predict the bounding boxes for each class of interest. So the problem with this approach is that we've got about 2,000 object regions that we find using, say, clustering. And then we have to pass it through all these pipelines. And that becomes super expensive because we have to process, we have to take those one image and basically effectively generate 2,000 corresponding images that we kind of have to warp. So it's super slow. And then fast RCNN and faster RCN, they work a little bit differently. They work on having fast RCN makes this guy faster, and faster RCNN replaces the region proposal algorithm with a neural network model. So it's still a two-step process, and I'm just moving ahead here so that we don't get to not talk about other things. So I'm just going to show you this family on a side-by-side basis so that maybe you can appreciate what these three approaches. So here we have here's RCNN, where we say, take our image, go find the regions like clustering, then warp them, and then pass them through the pipeline. So super slow. And fast RCNN says, take the images, push them into this feature map space, and find the regions here. And in this region here, warp these feature map representations of the region using this ROI pooling. And this ROI pooling is kind of, it's like max pooling or pooling in general, but it's kind of a clever way of right sizing these regions such that the successive layers in our network, like a VGG net or AlexNet, are of the right size. So we do warping here at this feature map level as opposed to out of the image level. And so this is a clever idea. And then faster RCNN is a little bit different, where I said, so this region proposal stuff here was using, say, clustering. Here we've said, okay, let's do a region proposal model here based upon deep learning. And ultimately we can train these two steps together. So this is an example of bottom-up processing where we cluster from pixels up. And our faster RCNN is kind of a top-down approach where we say, look, we look at our image in a particular way. We apply a grid to our image like we did for windowing. Okay, so I want to, I'm sorry, I want to skip ahead here and talk about single stage models. And here we got great examples: YOLO, SSD, FPN, RetinaNet, and so on. And I'm going to talk about YOLO in particular because I think it's a great way for us to master the concepts, which would be important, I think. So here, and then we'll talk about the new age problems. So we're looking at one stage object detectors right now, where we take our image and pass it all the way through the network, and we get a prediction, either it's an object or not. So this is a typical architecture here. And so these one stage models came after these two stage models, but they are now the more dominant approach to object detection. This is June 2015. This is the YOLO paper, not the best written paper ever, but I'll try to give you a gist of it. And then we have single shot detections, another model. And so you can see that there's a little bit of a race going on here. YOLO V1, V2, there's other stuff going on, feature pyramid network, RetinaNet, and then we got YOLO V3. And so there's a lot of competition, co-opetition, amazing things going on. And so YOLO V3 is basically saying, look, can I take all this stuff that has been learned here and can I shove it into YOLO V3? So that's YOLO V3 says, hey, I'm going to take all that amazing work that was done and put it into one thing, and that's YOLO V3. So YOLO V1 is a very simple model. It's very easy for us to relate to. Here's our input image, and then we can pass this through a convolutional neural network like Google.net or VGG or AlexNet and so on. And then we pass these, we pass our image in, get feature maps, and then we pass these feature maps along, and then finally we have our fully connected layer here, and then we reshape to get our output feature map. So the output feature map is a 7x7 grid by 30. And why is it 30? Because we're looking at the Pascal VOC data. We've got 20 classes in the Pascal VOC data. And so here's our 7x7 grid here. And each of these cells in the output feature map here has a vector of 30 values associated with it. And so this is our vector here. And this vector is composed of three main components. There's a bounding box component, the first 5, another bounding box component, and then there's the 20 classes. So previously I said, if we were asking this cell here to predict if there's an object here, and what's the class of the object, and what's the bounding box for the object, we're asking a lot. We're saying, look, these objects, they're all the same shape. They're all the same dimensions. So we're asking a lot. But we know that objects come in various shapes and sizes. And so with YOLO, we say, look, let's try to be a bit more flexible. Let's give this cell here 2 chances to predict bounding boxes. So that's so this bounding box prediction is not just the omnipotent bounding box that can predict everything. We say let's have two chances, two bounding boxes. Let's have two bounding boxes do the work. So here we've got 5 numbers. We've got 4. We got x, y, z, x, y, width and height, and we also have the class of the object for this bounding box. Or sorry, the confidence is an object in the bounding box. And similarly, we have another bounding box here with the same values, potential values, and we've got 20 values here, 20 classes here, one hot encoded. So then our task is to predict: is there an object in this region? If so, should it be part of bounding box 1? Or should it be part of bounding box 2? And in either case, what's the class of the object? So we're trying to, for each cell here, which maps directly back, you can see that there's a 7x7 grid here. Each cell is overlaid on top of its receptive field. So we've got a very easy way of doing the ground truth here, connecting these cells to the ground truth by looking at like we talked about previously, we can look at the center of an object and say, is the center of the object in this cell? The center of the object's receptive field is in this cell here, and do an allocation on that basis. So this is YOLO V1, and I'm rushing through this here, but YOLO V1 is kind of interesting because it's a very simple approach that is almost easy for us to program up in an afternoon. We generally train YOLO V1 using an existing architecture. It could be AlexNet, it could be VGGNet, it could be InceptionNet, and we take our transfer learning approach, we take our network here, and this is our classification head, and we just chop off our classification head, and then we add on an object detector head here. This is not fully convolutional because we got a dense layer here. This is also a dense layer here that's basically reshaped to be like a receptive field 7x7 with a depth of 30. This is our network here. It's got 24 layers in YOLO V1. And we take our predictions. So basically, we've got 7x7 grid. And then we've got 2 bounding boxes associated with each of these cells here. So that means that we've got 98 opportunities to find objects in our image. So that's just sound familiar because we had this kind of windowing and all that stuff. And so here we have 98 opportunities to find objects. So you can imagine that that's not much. And you can imagine, well, why is this YOLO V1 so important, or why am I talking about it so awesomely? Well, it's kind of intuitive, but it does a reasonable job, and it's super fast. And so I've got 98 opportunities here to find objects per class. And of course, then I'm going to have lots of detections, so I need to suppress them. And this works really fast. And you may wonder, how do we kind of talk about these things? This is an image here. This is the image name. And then this is the bounding box here. This is XML. This is the VOC markup. And this is our feature map here, our output feature map, if we were to visualize it. 7x7 grid. And then we've got the depth of 30. And then I've got the names of each value in these cell vectors. And we've got various ways of encoding these, and you can go through this in more detail. The videos have more detail if you watch them as well. And so we, as I say, we take each object. This is our object here. This is our bounding box for the object. And this is the center of the object. and we see that the center of the object lands in this cell's receptive field here, and then we compute an offset from the center of the cell to the center of the object, and we can get target values. So one thing that when we're doing object detection, there are a number of things that we have to be aware of. So first of all, in the case of YOLO, we say I only consider detections where the objectness of the prediction is 0.75. So I've got to be pretty certain there's an object here, and then I also just consider thresholds, class thresholds of 0.15. There's also an NMS threshold here for IOU saying suppress overlapping predictions or predicted bounding boxes if they overlap to the degree of say 0.5. So these are 3 thresholds I need to set in the case of YOLO, but they're similar for other approaches as well. When we look at YOLO, and when you look at the notebook, you'll see that when our network finishes, it makes a prediction. It'll predict a tensor like this. The tensor will be 7 by 7 by 30. And we can look at the 4th element of the 30 vector here. And this will correspond to, is there an object in the first bounding box? And you can see here, I've got 7 by 7 here. This is 7 by 7. And I'm asking the question, is there an object in the 4th field? Is the objectness score greater than 0.75? And it turns out that it's true here. This is the bounding box number 1. For bounding box number 2, we have to look at this value here, 4 plus 5. And we can see that, oh, there's a collision here. There are the 2 bounding boxes are predicting objects here. Okay, so then let me see here. So this is kind of YOLO in one diagram. This is my input image here. These are my receptive fields for my cells. These are the bounding boxes that for different objects. So this is a dog, bicycle, and there's a car here, believe it or not. And they and you can see the bounding box. The center of this bounding box here for the dog is below the center of the receptive field. So then from my training network, I'm going to say that the true target says that there are 3 cells here where there are objects. So my neural network now it needs to predict that there are objects in these 3 cells. And it should say that here is a car, here is a dog, and then I should predict the corresponding bounding boxes to be whatever, like this. So the network will output this 7 by 7 by 30 tensor, and I need to unpack it to compare it to my target tensor. And that's part of the tensor programming. So the loss function, which we haven't talked about yet, and don't get alarmed here. So we understand the classification loss. Unfortunately, this classification loss in YOLO was expressed as a mean squared error loss between the true target, true value, true classes and the predicted classes. Of course, you can think that this should be cross entropy would be a much more natural contender here. This made it simple to do the calculations, but a more natural one would be cross entropy. Then we have the regression loss function here. And the regression loss function, it looks like a mouthful, but really all you're doing is you're comparing the centers and the widths. And you're doing this for each region where you have an object. So we had 3 regions previously where there were objects, say somewhere like these. So there were just S by S squared is 7 by 7. B is, I got 2 bounding boxes in each of those output cells. And then I'm weighting these components in different ways in my loss function. There are different weights. So I have a weight of 5 associated with this bounding box coordinates. And I've got a weight of 0.5 with this component here. And I'm not sure with this one. I think maybe it's a 1 here. So what is this guy here? This is my confidence score. And here I've got these indicator functions. These are called masks or indicator functions. And what they do is saying, look, in the ground truth, is there an object? In the ground truth, is there an object? But here I'm looking for no object. I want no object here. This is my no object component here. So I recognize that some people are getting tired because it's nighttime in Europe, and I want to thank folks before you head out for staying with us. I know that it's early morning in Asia and past midnight in Europe, and it's just prime time in the US right now, I guess. And so I have these mask functions, and these mask functions are really important, and you will see them everywhere, and it's important to get our head around them. So the mask function basically is driven by our ground truth saying, look, for these cells here, for these 3 cells here, do these calculations. For the non-3 cells, do this calculation here. This is my no object stuff, and this is my classification where I have objects. So if I take that approach, then I can understand YOLO very easily. And so I need to define my network. And okay, so that's YOLO v1. There's a whole notebook and there's a whole library devoted to that. I didn't write the library, but I just used it. But I tried to unpack it so that we can actually process it easily. And so then I want to move on and talk about the state-of-the-art approaches, and in particular, I think you've gotten the gist about. You've got the hang of the feature pyramid networks and how we can use neural architecture search. We can search for a better architecture for those approaches. So I will share these slides so you can go through them more slowly. So like I mentioned earlier on, there's a lot going on in this field, and there are several hundred approaches to object detection, several hundred different architectures and loss functions, and it really is amazing. It's just hard to keep up, but there are a couple of common themes and successful trends that are happening. So this new wave here is driven by finding better feature pyramids using search, using grid search, or using NAS. And then there's the idea of transformers, which is kind of the new idea of 2020. Transformers have arrived. And this paper was introduced by Facebook. And I'm just going to give you an idea of, so you can see that it only has a map of 45 versus these feature pyramid networks of 55. But I think this guy here is really exciting. It just opens a new door to research and a whole bunch of new problems. We saw previously that our DETER, detection transformer, has a backbone, like our regular backbone. We take our feature vector, flatten it out. Each pixel then becomes has associated with an embedding, and we just run this through the transformer encoder to get a new embedding. And this encoder output is then passed on to a decoder, where we're asking a question here: are there boxes, object boxes, bounding boxes in the image? And so this is a fixed query size. In the paper, they set this to 100. So they say there is a maximum of 100 regions or objects in this image. And then the loss is kind of different in the sense that, first of all, my network is going to make some predictions and say, hey, I'm going to predict bounding boxes. And I need to, first of all, match the predictions with the ground truth. And that's it's called a Hungarian match. It's a bipartite match. So I'm trying to map these predictions. So I predict a bounding box. These are my predictions. And these are my ground truths. And let's say I only have 2 ground truths. So I have to figure out what's the best match for these guys here. So it's a sort of an optimization problem. So I take the output of the network from the transformer, and then I do a matching. It's a bipartite match, and then I compute my usual multitask loss function. So I've got my CXE component, and I've got my MSE or L1, L2 components. And also here I've got this GIOU, which you can read about elsewhere. It's a generalized intersection over union. It's a more gradient friendly metric. When IOU is 0, we don't do gradient descent on it. But GIOU always gives us a gradient, and it always tells us how we're doing. So this, and then this is it here, but I'm not going to, it looks at the bounding boxes and say, hey, how far is this bounding box from here? And is it getting smaller or better? And that's GIU. So I know we're over time. I'm going to take 1 minute to explain this here. So if you're familiar with transformers, then you know that you can take a word or a pixel. Our pixels are our raw input here. And then we can take our transformer layers, and we can look at the self-attention associated with this guy here. So this pixel here, and we say, if we look at self-attention between this pixel here and all the other, let's say, cells in our feature map here, then we see that this cell here is very attentive to these neighbors here. And similarly for this guy here, this cell here, we're very attentive to to these values here. So we have this idea of attention. We can try to understand what's happening here. And in addition, we have 100 slots where we can actually predict, is there an object, and what is the object? And here we're trying to say, look at the 20 slots, and we're trying to say, which regions are these slots working on? So we see that this slot here is focusing on objects here. It's looking at small objects here, whereas this guy here is looking at small objects over here. So each query has a role to play in this network. So the nice thing about this approach is that we don't have to do non-maximum suppression. We don't have to specify the granularity of our step size when we're doing windowing or we're doing anchor boxes or anything like that. And in the notebooks, I have a notebook that will build a logo classifier, a detector for you using DETR. And they're also, and so these are 3 notebooks here. Here's a demonstration notebook here. Here's the logo detector. Here we just kind of break down the results and kind of see what's happening inside. Okay, so let me just summarize in 2 minutes, and then we can be done. And if there's questions, we can take those as well. So I think the key summary slide here is that object detection is a very active field. There's some amazing progress, and the applications will just will step up over the next few years as we do a better job of detecting objects. And these single stage detectors are overtaking two-stage detectors very, very quickly here. And efficient det is one of the state-of-the-art approaches. And so if you were to go off and do object detection today, I would say go do this, because it's really good, and also it's very fast. And Detour, if you want to do some research, this is an amazing place to start. It's not easy. You need a tremendous computational power to train these transformers, as you well know. And so this is the other graph you should look at in terms of computational power. And there are a variety of libraries out there, like all the deep learning systems frameworks like TensorFlow, PyTorch, MXNet. They all have little zoos of models that are pre-trained that can be used, and then you can use smaller footprints to deploy on edge devices, or use full-blown models on super high-powered GPU machines to do detection. And so I did have a challenge here, I think, for you guys to work on. And in the notebooks, there are quizzes if you want to go do them, and there's some answers as well. So you can entertain yourself for a few days maybe. And so the big thing here is that we have moved away very quickly from a five-stage pipeline to a one-stage pipeline. And even in this one-stage pipeline here, it's getting to be very minimal input from experts. And so this is hugely exciting. And so there's lots of ways to look at things here. One thing I want to point out here, this is a website here. This is Research Papers with Code, which is a great resource if you wanted to maybe see how things are doing, and if you wanted to publish your work and benchmark it, then I would encourage you to go here and as a starting point. So if you have time, read this paper, Efficient Det. Read this paper. It's another one I didn't talk about, SpineNet. Here's Transformers, read that. And I didn't talk about a bunch of things. And here's a challenge. Build YOLO from scratch. It might take a day or two. And if YOLO is seems like really easy, just add on a few more layers and do a single shot detector. These are all one stage detectors. And this book here is awesome. And there's a chapter here, chapter 13, and in particular, these sections here will help you bootstrap you here very well. And so use your favorite framework, be it PyTorch, TensorFlow, Keras, MXNet. The book actually has MXNet implementation here. So that will help you quite a bit. Okay, that's it, guys. If you have questions, Penyang, can you switch on the chat here so we can see that people can ask global questions if they have questions?
Let me try.
You can.
Everyone, yeah. Now everyone can send comments, a message publicly.
Okay, great. All right, thanks. Okay, so are there questions? So like I said, we're compressing maybe a 45-hour lecture series into, let's say, 2.5, 3 hours. So we may have lost some signal on the way. I apologize about that. But hopefully you got a gist of things. If you're new to the field, maybe it's like maybe a starter. And if you're a veteran, then maybe you kind of caught up on some things. Any questions or comments?
Can you hear me?
Yeah, go ahead. I can hear Sam.
Thank you. My question might not necessarily be directly related to what you taught us over the last 3 hours, but it's related to object recognition. Many years ago, I heard a story when people tried to build an image recognition system which tried to recognize military equipment versus non-military equipment. And it turned out that it worked perfectly because it noticed that all tanks were on the snow and all cars were without snow. And apparently, this problem remains even today, that a lot of image recognition fails because it takes into account background and surrounding objects. This is not necessarily a bad idea. For example, if a child holding something in his hands is probably a toy gun, and if you see a soldier dressed in fatigues holding something in his hands, it's probably a real gun. So surrounding objects are not necessarily irrelevant. However, it seems like in many cases it might be irrelevant. So my question is, why not just augment your training data set with every true object surrounded with different backgrounds? Like if you have a picture of a car on the snow, just take this image and replace snow with grass, something like that. Is this a stupid idea? Is that hard to do? Why do people do that?
Yes, not a stupid idea, and people do it. And so, especially in the 3D world where data is even scarcer. And so in 3D world, you can actually splice in objects more naturally sometimes. And so if you think about gaming and you're always rendering, you've got graphics, you're always rendering objects in a realistic world setting. And you're trying to do that in a 3D world with physics. And so there's a lot of work on this. So I guess, first of all, so getting data and getting labeled data is extremely difficult. And a few years ago, people got really clever because they didn't have maybe deep pockets to go out and build data, especially LiDAR data and other types of data. So there's a game called Grand Theft Auto, where people started, like that game is really amazing because a lot of the graphics are very photorealistic. So they would go out and scrape Grand Theft Auto for training data and train detectors on that basis. And so today there are a number of frameworks that actually, there's a framework called Carla, C-A-R-L-A, where it's a simulated world where it produces 2D images and 3D point clouds in a simulated fashion. And you've got artificial places where you drive in suburban areas, rural, downtown, all that stuff. So, and the tasks are, you have to kind of drive from A to B without colliding with other objects. And so a purely artificial world. And so in that kind of setting, you can do whatever you want. You can have snow, or you can have dark. You can change things around. It's all parameterizable. In addition, so people work in this kind of artificial world, and then there's a whole field called it's called sim real. Go from simulator to real. So they learn stuff in the simulator, and then they say, oh, let's go and put this into a real car in the real world and see how it works. So there's a whole subfield around this as well. And so they take the kind of what they learned artificially on artificial data and then apply it to real world data. And of course, it doesn't work that well, but it's called survival as a student and getting your PhD done and all that good stuff. But there's some interesting work to fall out of it as well. And in addition, like I said, people have been looking at how to artificially drop in objects into, say, a 3D world that kind of look natural. So so it's like a deep fake for images or point clouds. And so in that sense, you could maybe create artificial snow scenes or fair weather scenes and so on. So, but I think the simulators like Carla is really, and there's many more as well from, there are maybe 4 or 5 frameworks that provides such functionality. And it's a great space to try out different algorithms if you don't have access to deep pockets or to self-driving vehicles and frameworks. So I don't know, Sam, does it kind of get to your answer a little bit?
Yeah, thank you very much.
Other question? Are we all just tired? Bored? All right. Well, I will share the slides in the coming days. And if you have questions, feel free to reach out. And I guess I'll be attending the conference as well. So you can always catch me there too. So I hope this was useful. I hope you got something from it and maybe learned a few things. Oh, and don't, yeah, I guess we have the Huawei app, I guess, the Huva app. Maybe you can leave some feedback on the tutorial there. I understand that we're very hungry for feedback on how these tutorials are, if they're useful, effective, how they should be changed maybe as well. Should they be longer, shorter? Should they be like just pure coding experiments, hackathon-like stuff, or so, all right. Other comments, questions, feedback? Yep, there's an open mic right now. So, okay, then I hope, so as I said, there are pre-recorded videos. In the pre-recorded videos, the tempo is much better. I get to cover two-stage models more comprehensively. I cover one-stage models also more comprehensively as well. And then we don't get into too much detail about the more recent approaches. So that if you're kind of want to get more background on some of these things that we skipped over, those videos have a lot more. And then of course the notebooks are a great resource as well. And the notebooks cover everything from basics right up to the latest approaches. And we have this kind of logo problem as kind of a quintessential problem. There's also a balloon problem as well. I'm riffing off another person's work repo for efficient debt, and they've done a great job of taking a balloon detector, or no, balloons and the shape detectors. There's a whole bunch of interesting little sub problems, but these are great starting points for training your own detectors. And then of course, if you want to do research, then I think you need to go back to YOLO and unpack that and work with that to kind of move forward. And if you want to, sorry?
Yeah, those videos, will they remain online indefinitely? The video and the document you shared?
I think you need to vote. You need to vote. If you don't vote, you don't have a voice in this matter. So you should ask. I mean, you should vote. Yeah, so maybe, I think so. I don't see why not.
Okay.
I've signed away my life here for these things already. So I think that they can, I think they should. I mean, I think it'd be a great service to the community to kind of,
yeah.
There are lots of great tutorials here.
I'm just afraid that they will remove them after the conference and we need to download them right away.
Nah, it's okay.
Okay, good, thank you.
I mean, I have a personal copy anyway, so if people don't want.
Oh, okay.
Copies.
So if they remove them, you will share them again.
I don't think they're going to remove them, but I mean, I hope not. I hope they'll make them available, I guess. That's, yeah. So yeah, watch the videos, read the slides. The slides are like a little, there's going to be probably like a few hundred slides in the deck or more than maybe you'll appreciate, but it kind of teases apart the different approaches and hopefully also breaks things down so that you can digest them and go out there and build your own. And like I said, if you want to deploy these systems all the big frameworks like TensorFlow, MXNet, PyTorch, they all provide very easy to deploy type models and frameworks, so that you can deploy a model on a Raspberry Pi. And so, like I said, it would be great to get down to a 3 meg model, but typically that's not really that useful. And so typically you're running in the range of 10 to 30 meg to kind of do something really useful, and you're running in the order of 100 meg to get something really useful. And so what's really awesome right now is like going from 5 steps to 1 step. That's a huge gain here. And so therefore it's becoming easier to take these approaches. These are more commodity-based systems right now almost. But as I say, the frontier is moving forward pretty quickly, which is awesome as well. So I guess then I will wrap it up here. And thank you for your attention. And I guess I'll see you online. You're welcome. And I'll see you at the rest of the conference over the next day or so. Thank you, guys. Ben Yang, thank you so much as well for your help.
Thank you, James, for the amazing tutorial.
I hope you learned something as well.
Yeah, sure. A lot of things.
Great stuff. All right, so I'm going to end the meeting here, and I think if I end the meeting, then we just exit gracefully.
Yeah.
Thank you, guys. Have a good evening.
Thank you.
Or
yeah,
good morning, or good night's sleep.
Yeah.